Morning, Joshua.
Hello, can you hear me?
I can hear you. Can you hear me?
Yes, sir.
Hello, good morning. Good morning.
Hello. How are you all doing?
Good
I'm good.
yourself?
Good. Sorry for the delay. Thanks for being patient. Good morning. Good morning, Jocelyn. Okay, so we're gonna. I hope you're all doing okay. How did it go? If you were able to try, how did it go with the 9.6?
Good.
Is okay so far?
Yeah.
Okay. Um, And well, we're going to do two more of those problems. They're a little bit um, unique. And so I wanted to help you with those two and also look at our last section that we're going to be able to do, which is 9.4, which is the fairly, well, I say it's short and then it turns out not to be short. So I'll just say, I hope it is relatively short. So let's begin. And I'm going to go to so can you all see the WebAssign page?
Yeah.
Okay, so we're gonna go to and 9.6. And I wanted to help you with two problems, and that is number 6 and 7. Okay, well let's look at number 6. And I did write this, as I told you last time, I did write these problems out on my notebook, so I'm going to use that again. Hope that doesn't cause too much grief for anyone. So let's see here. Okay, so if you haven't written the problem down, well, you'll see it on my notebook anyway. So here we go. And number 6 is right here. So let me try to cover up all this other stuff that looks kind of may look intimidating or distracting. I don't know. So, okay. Okay, so number 6 here, we have this is the equation of the sequence, n factorial over n to the nth power. And of course, the summation of all the terms from 1 to infinity, which makes this a series question, yeah? So the first thing we would normally do is just look at the limit of the individual terms of the sequence. And I did, so if we do that, we would write what n fact, well, so what I did here was just rewrite, I should say, what n factorial is and what n to the nth power is, just to get a sense of what would be the informal, if we did it informally, what kind of tendency or feeling would we get about the limit of the individual terms of this sequence. So, well, right now, if you just put infinity in and infinity, you're going to get infinity. Well, this would be infinity to the infinity. Okay, we'll say that's infinity. We would end up with infinity over infinity. And we couldn't use L'Hopital's rule here because we do not know how to differentiate a factorial expression. And this has its own problems as well. But we don't need to go that any further than that. So let's look at it informally. And what I did here is just start to write out what n factorial is by the straight definition. And so depending on what way we write it, we could say starting at 1 times 2 times 3 times 4. and so forth, on to n minus 1 would be the second to last factor. That's an n right there. That and sorry, so this is just an n right here, and then it and so in the denominator, n to the nth power just means n times n times n times n times. So if we were to look at informally what the limit of these terms of the sequence would be, well, you can see what's happening here is these would cancel out, n divided by n minus 1 divided by n, like that. If you were to, let me put it another way, 1 over n, 2 over n, 3 over n, 4 over n, and so forth. As you go out to larger and larger numbers, n is going to dominate the 2 on top, and n is going to dominate the 1 on top, because n will be larger. Say we're at the 200th term, and we want to know what is the 200th term of the sequence. Well, then we would be going out to all the way out to 200. And so here you would have 200 factorial, which would be 1 times 2 times 3 times 4, all the way up to 199 and 200. Here you'd have 200 times 200 times 200 times 200, and that would be 200 times. And then these would divide out, but the rest of them, it would be 1 over 200, 2 over 200, 3 over 200, 4 over 200, like that. The last one would be 199 over 200. The denominators for each, if you split these apart and think of this as a fraction, 1 over n, 2 over n, you can group them up like that in our minds. And all of these denominators are going to be bigger than the numerators. So these are all fractions less than 1. Like 1 over 200 is less than 1. 1 over 200, 2 over 200, and so forth. So all these fractions would be less than 1, and when you multiply them out, numbers that are less than 1 times another number less than 1, and you keep doing that, the answer just gets smaller and smaller. So in a logical sense, these terms, as you go out further and further, the terms are going to get smaller and smaller. And that's an informal way. But so informally, we could say the limit as n approaches infinity of n factorial over n to the n converges to 0. And I also did a little mathematical proof of that, but I don't think we really need to go that far. Because we're going to end up using the ratio test anyway. And when we use the ratio test, we don't have to formally prove that first step of showing that the limit of the individual terms go to 0. We don't have to go with that first step that we normally do. We can just dive right in to the ratio test. So although I did prove it here that it does actually equal 0. And then we would have had to, that means we would not be able to use the nth term test for divergence, and we would have had to look for a series test anyway. And then the series test that we would eventually get to that we would have to use would be the ratio test. So if anyone wants for me to go over that, I can go over it. But I think we can just go on now and go right to the ratio test. So all I tried to describe so far is that if we were to take that first step and look at the limit of the individual terms of the sequence, then we would get 0 either formally or informally, and then we would have to proceed anyway. So we're just going to proceed, and now we're going to go to the ratio test, and here we go. So the ratio test, of course, is we look at the limit of the n plus first term and divided by the expression for the nth term of the sequence, like we did last class. So what you do, of course, this is the formula for a sub n for any nth term. And that would be underneath, but instead of writing it underneath as division, I already multiplied it by the reciprocal. So instead of n factorial, we just have it reciprocated here. And then right here, we would have the n plus first term expression for the sequence, which would be to take the original formula which is this n factorial over n to the nth power. And now we want the n plus first term expression, which is just wherever there's an n, you put the n plus 1. So there's 3 n's in this formula, so we're going to put n plus 1 3 times. And this would be in the numerator, and this would be in the denominator. And then we would want to take the limit of all this, and that's the ratio series test, the absolute value of that. And then, and to begin, then once you have this written down, you would change this from division to multiplication, and that's when we would reciprocate it, and that's what we have up here. So any questions so far?
No.
Okay, everybody good, I hope? Okay, so let's go on, and now we're gonna put this n plus 1 factorial, and we're gonna put it underneath it, this n factorial, because that whole purpose of the ratio series test is when you do write the n plus first term divided by the nth term expression, these factorials will divide out. And that makes it much more likely for us to be able to find the limit. And then based on comparing it to 1, we get convergence or divergence, or the test fails. So that's the nice thing about the ratio test, especially when we have factorials. The n to the n's, that can work out nice as well, because we can cancel the most difficult part of the formula out, and then we have less to deal with in our attempts to take the limit. So anyway, so now I'm simply going to write n factorial under this one, which is what we have right here. And then n to the nth power divided by this. But splitting this up, we have n plus 1 to the nth power, and then n plus 1 to the first power. So I just split this exponent n plus 1 into this right here. So remember, if you multiply a common base, a base times the same base, you add the exponent. So n plus 1 would be the exponent here. And the reason we want to do that is because if we're looking ahead, we'll have this extra n plus 1. And when we divide this out, you're going to have an extra n plus 1 on the top, a factor of n plus 1, and then they're going to divide out. Again, in our attempts to reduce this to a simpler and simpler form. So any questions there?
No.
Okay. So now we have, so right here, n plus 1 factorial over n factorial. I hope we're comfortable with this simplification process, which is to take the larger factorial expression, n plus 1 is larger than n, and start to write this larger factorial expression and start to write down its factors. until you get down to the smaller expression, and it doesn't take long, because if you write n plus 1 factorial and start to expand it, you get n plus 1 times n times n minus 1 and so forth. But we already got to n, so there's no need to keep expanding n factorial out because we know we have an n factorial on the bottom. And so those n factorials will divide out. And we have an n plus 1 here divided by, I just moved this n plus 1 factor from the denominator and moved it underneath this one. So just to make it hopefully more apparent that we can divide those out to 1. So now all we have left is, so this is gone, this is gone, this is gone, and all we have left are these, this in the numerator and this in the denominator. They both have exponent n. And right now, remember, the whole idea is we're trying to get a determining limiting value for this limit and then compare it to 1. That's the whole design strategy behind the ratio series test. So if we would have tried to take the limit anywhere along the way, we would have had a whole bunch of infinity over infinities and so forth. And again, L'Hopital's rule is not when you have a whole bunch of infinity over infinities, you only would have 1. And then we would have a real tough, oh, it's not possible to differentiate a factorial expression. So anyway, so we end up with this and this. They both have the same exponent, and so we can put this and this together as one fraction, one ratio, and have the nth power written only one time. So this still means n to the nth power and n plus 1 to the nth power. And everything else is gone. So now we're getting down to a simpler and simpler form. We have limit as n approaches infinity of just this. Well, here we would have infinity over infinity to the infinity. We can divide this out. We can divide every term by n. N to the first power is the highest n value in the denominator. So we could divide everything by n. And when we do that, in our attempts to find the limiting value, trying to get a determining limiting value, then we have this right here, because the n divided by n is 1. N divided by n would be 1. And 1 divided by n doesn't reduce. So that's why we would be right here. Any question going from this step to this step?
No.
Okay. All right. So now what happens if we take the limit now? If we get a determining value, well, then we're very thankful and we're done. And if we get a friendly indeterminate value, well, then we try to use L'Hopital's if possible. If it's an unfriendly indeterminate, well, then we have to use our strategies of trying to manipulate the expression so that we can change it into a friendly determinant or get a determining value and be done. So now we're ready to try to take the limit right here. So if we take n approaches infinity, 1 over infinity is 0, plus 1 is 1. 1 divided by 1 is 1, of course. And then we would have 1 to the infinity power. So 1, which is what I have right here, this part.
Sorry, how did you get the limit of 1 over 1 plus 1 over n?
Okay, good question. So back here we were only had this part left right here. And because when we take the limit as n approaches infinity right now, you would have infinity over infinity to the infinity. So what we can do is we can always take and just pretend we have an algebraic fraction. Just like if we have, let me make up a different one with numbers. If there's a mathematical benefit, we have it's mathematically correct if there's a mathematical need. We can take this whole fraction here and divide every single term by any number we want except for 0. And it's an equivalent fraction. So if we wanted to divide everything by 2, I don't see any reason why we'd want to, but it was certainly mathematically okay, because you're basically just multiplying the top and the bottom by a half, which is the same as multiplying this whole thing by a 1. But that doesn't really serve much purpose. But if we wanted to, we could. If we wanted to divide everything by 3, we could do that as well. Maybe that's more worthwhile than dividing everything by 2, because then you would get 1 over 1 plus 1/3. And that may be open to debate if that's any more beneficial than this one. It really isn't, but it's still the same answer. This reduces to 3 over 4, of course. This reduces to 3 over 3 plus 1, which is 3/4. And by doing this division of 3, if there's a reason why you'd want to do it, then we can. And what would we get? Well, 1 over 1 plus 1/3 is 4/3, and that equals 3/4, which is the same as up here. So I hope I'm trying to make it understandable why, first of all, to show you that it's mathematically correct to divide a fraction with terms and divide every single term by the same object or the same number. So in this one, if there's a mathematical reason, we could take every term and divide it by, we could divide everything by 2 again, or by 3. I don't think it's going to serve much purpose, but we certainly can. But if we wanted to, we could divide everything by x, as long as x is not equal to 0. So we have to make some declaration. This will not be true if x equals 0. We'd have to say when x is not equal to 0. When we end up dividing by n, like I'm going to show you momentarily, remember, n starts out at 1 here, somewhere from the beginning. So as long as we're going out and as we go out to n approaches infinity, n are positive integers, so we're not dividing by 0 in any way. So if we decided to divide everything by x, if there's a mathematical benefit to it, then we would get x divided by x is 1, x over x is 1, plus 1 over x. And just like this was equal to this right here and this right here are mathematically equivalent, except at x equals 0. So we do the same thing then, because for this limiting question, there is a mathematical benefit to divide everything by n. And when we do that, we get the same thing as this right here, except these will all be n's instead. Is that okay, Jocelyn?
Yes.
I don't know if
Thank you.
yes. Did I answer your question, or did maybe I misinterpreted your question?
No, you answered my question.
Okay. So now, Jocelyn, think about it. Is there going to be a benefit now to writing this like this, or in this case, the same thing but with n's? If we try to take the limit now, what's going to happen right here? Well, we won't get infinity over infinity anymore. We will get 1 over 1 plus 1 over n. And do you see how this all becomes 1 right here then, Jocelyn? Is that part okay?
Yes.
Okay.
Yes.
Now, someone might say, well, could have we used L'Hopital's here? Well, when we take the limit, we're supposed to use L'Hopital's rule when the whole value is infinity over infinity, and we have an infinity over infinity, but it's to the infinity power. So there may be some ways around that, twisting this to also get 1 to the infinity. We could maybe do it informally, and that would also get us to 1 to infinity. But either way, we get this 1 to the infinity power, which is an unfriendly indeterminate. So now we need to manipulate either this statement, but this statement right here came from this one over here. So now we're going to say, oh, we got 1 to the infinity. It's an unfriendly indeterminate. Now we need to do something to rearrange this expression or this one. I chose to start back with this one instead of this one. I'm sure we could have done either way. It works out. I think this looks a little less sloppy or messy algebraically, so I just chose to go back to this expression that kind of got us to an unfriendly indeterminate and work from there. But there is more than one. You could also work from right here. So I wrote here, go back to this expression, limit as n approaches infinity of n over n plus 1 to the n, which is again this right over here. And now when we have 1 to the infinity, that unique unfriendly indeterminate, the strategy that we had learned is to rewrite this as an equation statement and call it some letter or some word. I use the word answer. When we first were introduced to this in section 8.7, and we could still write the word answer or any letter, just don't use n or something. So we let this limit that we're trying to get the determining value, whether it's infinity or it's a finite single number, it won't be negative infinity here in this particular case, but and it won't be oscillating either, but it could be on some other problems. Name it something, the answer, and this is what we're seeking to get, this determining value. And the strategy is you write the equation and write down something here as the answer to this limit question so that you now can perform an algebra, a mathematical operation to this equation in order to help us get this n out of this exponent position and down below, which gives us an additional opportunity to remove the unfriendly indeterminate portion of the problem. So to bring this n down in front, we can use the advantage of logarithm in their properties. And so we could take the log of both sides of this equation. You could really use any base you like, log base 10 or log base 4, but it's just cleaner to use ln. But we could also use log. So now that's why we have here ln of y equals the limit still of the natural log of this. But the whole reason we're putting the ln there again is so this n can come down in front and as multiplication. So that's what I have here. ln of y equals the limit so we have the limit right here as n approaches infinity of n times the ln of n over n plus 1. So we already moved this n down and put it in front. And see, now we can no longer get 1 to the infinity. Yeah? So if we did stop right here and took the limit, well, n would be infinity right here. Infinity over infinity, we would have that same problem again. And you could divide everything by n like we did right over here. And you would get 1 again. And ln of 1 is 0. And we would have infinity times 0, which is another unfriendly indeterminate, but a different kind. And so in that case, then you want to move one of these two multiplied objects from its position of denominator or numerator and move it to the other position and see what happens. So if this one's just a simpler object, or the n, so it's easier to move the n underneath, and when you move it underneath, it'll become 1 over n. And now that will get us, or that's in our attempt at least, to get this into at least a friendly indeterminate, so we could use L'Hopital's rule. Any questions so far?
No.
And so this is what makes this problem more of a challenge, is the situations that we're on right here. I mean, these have their own challenges of reducing and everything, but this is the reason I wanted to wait on this problem, was because what we're doing right here. So if we now proceed with that, the 1 over this n over 1, when you move it underneath, it's going to become a 1 over n. So then I think I did, yeah. So I did a little thinking in my mind, apparently, before so what I just did is I just did what I told you, and I said that if we leave it like this, we'll get infinity times 0, which is not, that's also unfriendly. So I said to myself, I'm going to move it underneath, and so let me just write another part right here. So right after this, we have the limit and we have the ln of n over n plus 1 over the 1 over n. So that's doing exactly what we said here. Move this underneath, and when you move it from multiplication to division, you have to reciprocate it. Of course, if you were to bring this back up from division back to multiplication, it would be times n again. If we try to take the limit right now, let's see what would happen. Well, 1 over infinity is 0, approaches 0. And here, you get infinity over infinity. If you use either L'Hopital's rule or divide everything by n, you get right back to this inner, well, this right here again, which is this right here. And we would get 1 over 1 plus 1 over infinity, which would be 1 over 1 plus 0, which would be 1 over 1. And we would get natural log of 1, which is 0 itself. And then we would be to a friendly indeterminate, 0 over 0. Any questions right there?
No.
So now we need to contend with this issue of 0 over 0. We could go, if we go, we can go right to L'Hopital's rule and differentiate this and differentiate this. the derivative of 1 over n is negative 1 over n squared. But we need, when we take the derivative of this right here, we're going to get a mess if we leave it like this. If we leave it as ln of n over n plus 1, when we differentiate that, we're going to have a mess right here. It would be 1 over the inner function times the derivative of the inner function, and that derivative of the inner function would be a quotient rule, and it's a real mess. So the most important reason I wanted to help this problem was was precisely the next step from right here. This we've kind of done from time to time throughout the course, and this little confusing part when you need to decide to move this underneath or leave it, we've done that before, and we've gotten to this point, and we've had to use L'Hopital's, and when we took the derivative of the top piece and the bottom piece, then things would work out. And we would get a determining value, and then we would set ln of y equal to that determining value, exponentiate both sides by base e, and we would get our limit value. What makes this problem extra challenging or interesting is this part right here. If we use L'Hopital's rule right now, it doesn't make anything better. It just makes it worse. It makes it a mess. So this next step is the main reason why I wanted to help, okay? And so instead of differentiating this, because it'll get ugly very quickly, we can do this first. So before we use L'Hopital's, we can rewrite ln of n over n plus 1, and we can use another one of the properties of ln. And that is this property. If we have any logarithmic expression that has a ratio in it, then if there's a mathematical benefit, we can write it as a subtraction of the ln of the numerator minus ln of the denominator. So doing that, we're going to write right here, everyone, we're going to write, instead of differentiating this, first we're going to use a property of logarithm and write ln of n minus ln of n plus 1. Okay? And we can differentiate the denominator, that we can leave it like this, or we can bring it up and use the power rule. And then once we do expand this out to like this, then we can differentiate that as well. So right here, everyone, I took this ln of n plus 1 and came down right here and rewrote it as ln of n minus ln of n plus 1. Any questions right there?
No.
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 Now differentiate this. Instead of differentiating it like that, differentiate it like this. So, so I'm sorry. So what I realized from right here to the next line, if you differentiate this, you're going to get 1 over n and 1 over n plus 1. And that is not going to be as helpful, because realize the derivative of 1 over n, the derivative of 1 over n is the same thing as the derivative of, move it up, n to the negative 1 power. And the derivative of that using the power rule would be negative 1 times n to the 1 less, which is negative 2, which is the same thing as negative 1 over n squared. So the derivative of this 1 over n, which we just showed right here, is going to be negative 1 over n squared. So, which I wrote right here. Oh, can't see it. The derivative of 1 over n, which is the denominator, is negative 1 over n squared. And then what I told myself was, well, I would like, if possible, when you differentiate the numerator to get a negative 1 over n squared so that it can divide out, and then you will have reduced this problem to a point where you will get a determining value. And if we leave it like this, which was a good attempt at thinking of that, but if you differentiate that, you would get 1 over n minus 1 over n plus 1. And if you were to then if you were to take the limit, you would get 1 over infinity minus 1 over infinity, which would be 0 minus 0. You would get 0 on the top, and you would still get 0 on the top, and the derivative of this would be this down here, as I told you, and 1 over infinity again would be 0 again, and you would still have to use L'Hopital's rule, and we wouldn't have really gotten anywhere. So then I told myself, well, instead of leaving it as ln of n over n plus 1, change that by doing this division right here and getting this right here. But it would be with respect to n instead. So that's this part. When we did it from way up here, remember we divided everything by n and we got this part right here. So that's what I did right here. I wrote ln of n over n plus 1, and instead of writing it this way.
Okay, so we're not using the log property?
We are going to, yes.
Okay.
It's just that before we use it, we're going to change ln of n over n plus 1, and we're going to change it to, and what did we say happens when you take n over n plus 1 or x over x plus 1 and you divide everything by x or everything by n? Don't you get this right here, Denise?
Yeah.
So what am I going to put right inside this ln? Instead of n over n plus 1, what are we going to write instead?
1 over 1 plus 1 over n.
Good. That's all inside the ln. What's in the denominator still? This right here, 1 over n. Is that part okay?
Mm-hmm.
Now, we didn't use any property of ln yet. All we did was divide this n over n plus 1. We divide every term by n, and we got this part. And there's still a ln there. And this 1 over n is still on the bottom. Is that okay?
Yeah.
Now, what would happen if we took the limit right now as n approaches infinity? What would this 1 over infinity be again?
0.
And all this would be 1 over 1 plus 0, which would be ln of 1. But ln of 1 is 0, and 1 over infinity converges to 0, so we would get 0 over 0 again. So we would have a friendly indeterminate again, which would mean we would use L'Hopital's rule. The derivative of 1 over n is still this right here, negative 1 over n squared. I showed you that right over here. And so if we differentiate this, though, this will be a mess. Not a terrible mess. I mean, we could leave it like that, and that would work. But I said, let's take advantage of the logarithm, another logarithm property, which is to write ln of 1 minus ln of the denominator, which is this part. And that's what we have right here. And then we still have to differentiate this 1 over n. Any questions right there?
No.
We could have left it like this and used L'Hopital's rule, and it would give us the same thing. I just think it's slightly cleaner to write it from here to here. Okay, now we're going to differentiate the bottom. The derivative of 1 over n with respect to n is this negative 1 over n squared, which I showed you over here. And now the derivative of ln of 1, well, ln of 1 is just, well, first of all, ln of 1 is just what number?
0.
0. And the derivative of 0 is still what?
0.
0. So good. So the derivative of this inside part right here would be zero from this part minus, there's the minus. And now what's the derivative of any ln? It's 1 over the expression. So it's 1 over 1 plus 1 over n. Is that part okay?
I thought it was the derivative of the inside.
You're right. So the derivative of any ln is, so the derivative with respect, say, to x of ln of x cubed, for example, is 1 over the inner function times the derivative of the inner function. And this would be the 1 over x cubed is weighting. The derivative of the inner function would be 3x squared. And now you would clean this up and you would get 3 over x or something. So the derivative of any ln expression, oh, I'm right here. The derivative of ln of 1 plus 1 over n will be first 1 over this, everything inside here, then times the derivative of what's inside.
Okay.
Is that cleared up?
Mm-hmm.
So we already said ln of 1 is 0, and the derivative of 0 is 0, and there that is. We don't really need to write it down, but there it is. Minus, because of this minus right here. Now, what's the derivative of ln of an inside, of any inside expression or function? It's 1 over the inner function, which is 1 over 1 plus 1 over n, this part, times the derivative of this inside. Well, what's the derivative of just this one by itself?
Negative 1 over n squared.
Yes, the derivative of 1 over n, very good, is the same thing we showed over here on my paper. The derivative of 1 over n, which is the same as this, which is this, which is this, negative 1 over n squared. Good. But first though, what's the derivative of what's the derivative of just this 1 plus this 1 right here, all by itself?
Oh, 0.
So yeah, you'd get 0 plus the derivative of 1 over n, but the derivative of 1 over n is the negative 1 over n squared that you just mentioned. So the derivative of ln of 1 plus 1 over n is 1 over the inner function, 1 plus 1 over n, times the derivative of the inner function. And the derivative of this inner function, the derivative of 1 is 0, and the derivative of 1 over n is negative 1 over n squared. There's really no need to write this 0 again, but we could. Any questions there?
No.
So now 0 minus, well, you don't need the 0, so you're just left with negative 1 over 1 plus 1 over n times, you don't need this 0, times negative 1 over n squared. And that may look a little congested, so I'll just write it over here somewhere as well. So this becomes negative 1 over 1 plus 1 over n times negative 1 over n squared and then what's all that divided by? Divided by the derivative of this part, the 1 over n, which was from this part. And the derivative of 1 over n is also negative 1 over n squared, which I had written right here. But I'll just write it on this right here. So also, on the denominator, the derivative of the 1 over n becomes negative 1 over n squared as well. And this is what we needed, because now what's going to happen to this multiplied negative 1 over n squared and this negative 1 over n squared? They're going to divide out to 1. So all we have left now to contend with is taking the limit of just this part, the negative 1 over 1 plus 1 over n. So and that's where I am right here. Now we have natural log of y, still that's been waiting all along, equals the limit as n approaches infinity of just this part. Yeah, because these divided out. There, I just have it written here. Any questions there?
No.
And now we try to take the limit and hope we don't get any kind of unfriendly or friendly indeterminate, and we get a determining value for when we now take the limit and try again. So if we take the limit as n approaches infinity now of just this remaining reduced simplified expression, well, negative 1 remains, 1 remains, 1 over n is 1 over a larger and larger number goes to 0, 1 plus 0 is 1, so we get negative 1 over 1, which is the determining limiting value. It's the single finite number of when we take a limit, we can get those types of determining values. Infinity, negative infinity only, an oscillating type that also diverges, does not exist or diverges, or converges if we get a single finite number, which is what we did. So this limit does exist. We do have a single finite number, so we can say the limit exists and we know it's negative 1. However, all that was from the very, very beginning when we had the 1 to infinity, and we had to use the technique to get rid of that 1 to infinity, which was by renaming this limit problem and calling it some single letter. And that's when we were right here, and we called the answer to this limiting question a single letter. And now we then had to take ln of both sides, and now we have then the ln of y has been waiting all along for us to get the determining value of this other side. We finally did. It's negative 1. So now we have natural log of y equals negative 1. Exponentiate both sides. by base e. We get e to the ln of y equals e to the negative 1. The e to the ln composes to y. And we get y equals e to the negative 1. But e to the negative 1 can be written as 1 over e. Any questions there?
No.
And what kind of situation? So now we finally have made it through the ratio series test, and we did get our determining limit value, which is 1 over e. 1 divided by e, if you put it in a calculator, it will be less than 1. So what does that tell us? When we use the ratio series test and we get the determining value to be less than 1, then what does that tell us about this this sequence when you add the terms up forever and ever? Or we can say series. Does it converge, diverge? Is the test? Can you imagine if we would have got equals 1 here, and then we would have had to use another test? That would have been a little bit maddening, but we didn't. Yeah. And so what does this tell us by the ratio series test when we get less than 1?
Converges.
Converges. So therefore, the series converges by the ratio series test. Any questions there?
No.
So I debated, as all teachers will debate, as you know, how far in difficulty do we go with concepts and homework problems, and this is one towards the edge of the line, if you will, but I felt it's worth going over because it does stretch us a little bit and show us there are some limits that we have to really go beyond what we normally do. And not only did that happen on this one, but then we also had to do one more extra thing that we normally don't, even on a messy extended limit problem, which is take advantage of another property of ln. And that's what we did when we expanded this to this right here. Yeah. So that's the reason why I wanted for us to challenge ourselves with this problem, because of those new, we're encountering new situations that we normally don't. But anyway, so if we go back to WebAssign, and number 6, and here is, we know it converges. We know the limit when we did the ratio test, it converged to 1 over e, and that's less than 1, which is why we said converges here. So then we have everything correct here. So it looks kind of harmless right here, a simple little n factorial over n to the n, but it did require some extra analysis to come up with the determining limit value. Okay, so yeah, a little bit nasty, but I think we need that, at least a little bit of it, from time to time at this level. Okay, so any questions before we go to number 7?
No.
Number 7 is not as messy as number 6 at all. It has its own uniqueness, and the uniqueness is not the -1 to the n plus 1. That makes it alternating. It's not the n factorial. We've dealt with n factorial several times now, and the ratio test is usually the nicest thing to use to get rid of the factorials, as we've been doing. The reason that this problem is a little bit unique is this denominator here. We've seen just 2n plus 1 or something in the denominator, but it's not just. So there's a considerable difference between this formula for a sub n, the n factorial over and we have this alternating piece. And then divided by, if we just had 2n plus 1, well, we've dealt with that kind of situation before. We could use the ratio test here, and it cleans up very nicely and very quickly, and we would be done in a short period of time. Now I realize I want to just go one little step further with this formula to help us understand how this is different, because this is the most likely piece that will cause us some confusion right here. So if we were to continue with this right here, and we were to write the 0 term, the first term, and so forth, this is supposed to be a 1. And let's see. For just this one, we're ignoring this one right now. So what would happen, Josh, if we put a 0 in right here in the denominator? We would get 2 times 0 plus 1.
1.
1. In the denominator, when n equals 1, what's 2 times 1 plus 1?
3.
And when n equals 2?
4.
Almost.
5. My bad.
Okay, no problem. And 3?
7.
And so forth. In the numerator, we would have, Josh, what would happen if we put 0 plus 1 here? 0 plus 1 is 1. What's negative 1 to the first power?
Negative 1.
Good. What's 0 factorial? Do you remember what that is by definition? 0 factorial by definition equals 1. So what would be the negative 1 times the 1 then, Josh?
Still negative 1.
Mm-hmm. How about when n equals 1? 1 plus 1 is 2. Negative 1 squared
1.
times 1 factorial. What's 1 factorial?
Still 1.
Times the 1?
1.
1. When n equals 2, 2 plus 1 is 3. Negative 1 cubed.
Negative 1.
And 2 factorial.
So times 2.
Because 2 factorial is 1 times 2 or 2 times 1. So you said for 2 plus 1 is 3, negative 1 cubed was negative 1 times 2 factorial is 2. So negative 1 times 2 is what?
2. Negative 2.
That would go here. One more. Put a 3 in. 3 plus 1, 4. Negative 1 to the 4th is positive 1. And then we put 3 factorial. 3 factorial. What's that, Josh? 3 times 2 times 1.
6.
Good. And 1 times 6 is what?
6.
6. These would be the first, starting n equals 0, which they tell us to. These would be the first 4 terms of this formula. So I think that's part of the reason that I wanted to, what's the main reason I wanted to do this problem is because it's easy for us, because we never seen something like this part right here before. So I want us to understand that it's not the same as this. So, oh, let me pick a different color. So what if we say, oh, let's do it again. a sub 0, a sub 1, which is n equals 1, and so forth. So, well, this formula right here, Joshua, and this formula right here, the numerator is exactly the same, isn't it?
Yes.
So won't these numerators be the same numbers when we look at this formula instead?
Yes.
So just to be a little bit quicker, we can use our answers from above, and the numerators are not changing from what we already did above there. Because the part that I wanted to show you is that 1 times 3 times 5 up to 2n plus 1 is not the same thing as just 2n plus 1. So let's now try this. So, okay, Brian, are you there? Brian, are you still there?
Yes, I'm here.
Can you help us with the denominators of this one? Let's see if they're the same as this or not. So this says, start multiplying 1 times 3 times 5, every odd number, until you get up to 2n plus 1. And how do you know where you're going to stop? Where is 2n plus 1 going to stop? It depends on what n equals. So
Okay.
what's the n value right here for the first term? N equals what? Right.
0.
So we're going to say 1 times 3 times 5 times 7 times 9 and keep going, unless we already went too far, and keep going up to whatever 2 times 0 plus 1 is. What is 2 times 0 plus 1?
1.
So that means we were already going too far when we said 1 times 3 times 5. We were supposed to stop here already, because this is where 2n plus 1 stops. When n equals 0, 2n plus 1 stops when you put a 0 right here and you get 1. So we should only have put a 1. So you're like, well, that's no different. Well, that's true. The first one's no different. Let's try the next one. When n equals 1, Brian, what goes in the denominator? 1 times 3 times 5, dot, 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 up to 2n plus 1, but n equals 1 this time. So we're going to write down here 1 times 3 times, keep going until we stop, unless we already went too far, then we have to back up. So what happens when you put 1 here? 2 times 1 is 1.
Yes.
I mean, 2 plus 1 is what?
Equals 3.
So that means we really should have only gone up to what? 1 times 3?
Yes.
And what's 1 times 3?
3.
3. And you're like, come on, Mr. King, that's the same as right here. Okay, so far. What happens when we put a 2 in? We're going to go 1 times 3 times all the way up to 2 times 2 plus 1. What's 2 times 2 plus 1?
That's 5.
So that means we're going to, in the denominator, we're going to write 1 times 3 times 5 and stop at 5. So what goes right here, it's 1 times 3 times 5. And that's what, of course, Brian?
15.
And now it's not the same as this anymore.
No.
First two terms were, but now they're going to change forever. So one more, put a 3 in, and we're going to go to 2, 3 plus 1, which is 7. So what's going to go down here, Brian? 1 times what?
3 times 5 times 7.
And whatever that multiplies out to, we put it right here.
It's 105.
105, okay? So that's the first, in my opinion at least, that's the first important piece we need to understand is that this, it's very easy for us to think that this right here means this. but it doesn't, okay? It means this down here. Are there any questions on that part?
No.
Now, in either case, even if it was this one, these are alternating just as these were. These, well, this might converge to something else. We'd have to look at it. But here, well, it's kind of misleading actually. But if right now it looks like these terms are getting closer to 0, and maybe they are, but we would have to do some further analysis, maybe do some more terms. We can't really use L'Hopital's rule. There is sort of an abstract way to prove that this limit as you go out forever. There is a way, which I did do it myself on my paper here, where you can prove that the limit does, I'm just looking at my note again, trying to remember what I did. And yeah. So anyway, you can prove that these terms do end up converging to 0. We could graph it and show it, but we don't really need to because you can kind of skip this first step. But if we did show it, it would be its own extra work. It would get equal to 0, which means it is possible for this series to converge or diverge. We don't get to stop at the nth term test for divergence and just say we're done. We would have to look at additional series tests, and we would use the ratio test, and that's what we're going to do. So now I'm going to take us to the ratio test and go from there. Are there any questions about this before I erase it?
No.
No.
Okay. Oh, what did I do? So now let's go to number 7. So that was in a sort of a discussion to get us to the point where we realize there is a chance this series converges, and we're going and understand what this bottom part really meant. It's not just 2n plus 1, it's the multiplication of the odd integers up to 2n plus 1 for each individual term. So now we're going to use the ratio test, and we're going to put this, the n plus first terms expression in the numerator and divided by the nth term expression in the denominator, which would be this. But instead of writing division, we're going to change it to multiplication and reciprocate this one. So this will be reciprocated. So this and this is in the numerator currently, and this is in the denominator. And when you reciprocate, then this part will be in the numerator, the 1 times 3 times 5 up to 2n plus 1, and these pieces will be in the denominator. And yeah, so using the ratio test, take the limit as n approaches infinity. Again, take this formula. By the way, I have it over here, times the, instead of divided by this expression, I changed it to multiplication and reciprocated it. And that's why we have the 1 times 3 times 5 up to 2n plus 1 in the numerator. The negative 1 to the n plus 5, which was this part, times n factorial, is now in the denominator here. Absolute closed absolute value, open absolute value. with a limit in front as n approaches infinity. What's this right here? This is the formula for the n plus first term of the sequence, which is the whole strategy behind the ratio series test. So wherever there was an n, we're going to put it n plus 1 instead to get the expression for the n plus first term. So right here, I have -1 to the not n plus 1, but instead of n, put n plus 1 plus the 1 that was already there. You could do that in your mind and just write n plus 2. It's up to us. Instead of n factorial, we put n plus 1 factorial. And here's that great reason when you have factorials that the ratio test works out so nicely, because at least relatively nicely, because now we're going to be able to simplify and divide out the factorial part of it. The denominator here, 1 times 3 times 5, I hope I've convinced you now that it does mean you keep multiplying the odd integers up to whatever n value you're at. And so in this case, we're stopping at the n plus first term. So when you go up to the nth term, that would be stopping here. And now you got to go up one more term, which is the n plus first term. And to figure out what that would be, you would put, instead of the 2n plus 1, instead of the 2 times n plus 1, instead of n, we're putting n plus 1. So this is instead of 2n plus 1, instead of n, we're putting n plus 1. So now distribute this, and we get 2n plus 2 plus 1 more, which of course is 2n plus 3. So when you go and you write the expression for the n plus 1, or n term for the sequence, then this denominator is 1 times 3 times 5 up to 2n plus 1. That would only be stopping at the nth term. Go one more term, which is when you put an n plus 1 in there, and then we cleaned it up and we got 2n plus 3. So that's why you have that right there. So again, this is the reason right here why I wanted to help, and to show something a little bit different here in terms of a formula for a sequence. Any questions so far?
No.
Okay, the rest works out pretty nicely, actually. We don't run into any trouble with indeterminate values. We're going to be able to reduce this relatively nicely and get a determining value right away. So that's good news. So let's see. We can write this base -1, that's an n plus 2 when we simplify it, divided by this -1 to the n plus 1. So I'm going to put this one underneath this one. N plus 1 factorial, and put underneath it n factorial, because we know we can reduce that. Which leaves us this expansion.
Do you have all that written down, or you're just explaining?
I have it all written down.
Okay, because I'm having trouble following because you're just
sorry.
talking.
Okay, sorry. So here is the n plus 1 factorial over the n factorial. Here is the 1 times 3 times 5 up to 2n plus 1, divided by the 1 times 3 times 5 to the 2n plus 1 times the extra term, which is the n plus first term, the 2n plus 3.
Where is that n factorial coming from on the top fraction?
This one?
No, just the n factorial on the second up
This one?
there.
That's coming from when we take a sub n plus 1, the expression for a sub n plus 1, and divided by a sub n. This part is the a sub n plus 1 expression. And then we would have to divide it by the a sub nth formula expression, which is this one.
Mm-hmm.
And so if we were to write all of this, Denise, underneath here, yeah, so we would have fraction, it would be -1 to the n plus 1, n factorial on the top, divided by 1 times 3 times 5 times all the way up to 2n plus 1. But instead of writing it as division, we're going to change it to multiplication, and then we have to reciprocate, huh?
Mm-hmm.
So what happens instead of having all this in the denominator and we change it to multiplication, then this gets flipped, right?
Okay.
So what was in the numerator here? I mean, I can write it here. -1 to the n plus 1 times n factorial. Underneath 1 times 2 times 3 up to 2n plus 1. Is my voice still sounding bad again? Is
It's okay.
Is it making any of that cracking noise?
A little bit.
Not too bad. Or are you just getting used to that new voice of mine, huh?
Yeah.
Okay. So does this part make sense here, Denise?
Yeah.
So you take the n plus first term, which is this part,
Mm-hmm.
so all of this is the a sub n plus first expression. That's this part on top. Well, also with this piece, sorry. Divided by the nth, the a sub nth expression. And what's the formula for any nth term? It's this original equation, right?
Mm-hmm.
And that's all underneath here now. Divided by the a sub nth formula or expression. Are there any questions on that part?
No.
Now, how do you take this messy fraction divided by this messy fraction? You could reduce it like this, but for most of us, it's easier if you change this from division to what?
Multiplication.
But when you do change it from this division of a fraction to multiplication, then you have to do what to this fraction?
Flip it.
Flip it. Good. So where is this 1 times 2 times 3 to the all the way up to 2n plus 1 going to be written up here?
In the numerator, no?
Mm-hmm. Correct?
Where's that 2 coming from?
This 2? This one?
No, the one on the bottom of the fraction.
This one?
Yeah, the 1 times 2 times 3. How did you get the 2?
Oh, I don't know. Because I lost my concentration. It's supposed to have been what? 1 times what?
3 times 5. Okay.
I am so sorry.
Okay, and then that goes in the numerator.
Correct. Is that part okay?
Yeah.
And then what becomes in the denominator here? Well, whatever was up in the numerator, huh?
Mm-hmm.
Which is now here.
Yes.
And then you would ask me, where did the n factorial come from? So now do you understand?
Yes.
Okay. And sorry, I wrote the wrong number here.
So-
So now we're going to reduce this, huh?
Mm-hmm.
I don't think we're ready to take the limit, are we? Of all of this,
No.
we're going to have a
No.
lot of mess here. We're going to have a whole bunch of infinity over infinity, infinity over infinity, and then we have this -1, which is an oscillating piece, and then that's gonna mess things up a lot. Yeah. So what do we want to do? Don't take the limit yet, because we're not going to get anywhere near to a determining value for this limit question, but reduce first, which was the whole point. By taking something so sort of complex here in terms of a formula with n factorial and these multiplication of these odd numbers down, and by using the ratio test, that is a really clever way of getting rid of the nasty pieces that cause us to get the indeterminate value versus a determining value. So now we will reduce. So we're going to put this -1 to the n, well, n plus 1 plus 1 is n plus 2. And so I might have just skipped that little step. -1 to the n plus 2, and then divided by what's down here, Denise? -1, not n plus 2, but n plus what?
N plus 1.
Mm-hmm. And when you have a common base, like if you have x to the 4th over x squared, well, you can reduce them mentally, or you can say, I'm going to subtract. 4 minus 2 is 2. Either way, you get x squared. So when you divide this out, you're going to do the same idea. You have the same base. Subtract the exponents. That's one way to answer this. You could also do another way, but n plus 2 minus n plus 1 and then simplify this and you get minus n minus 1. So what's going to be left here, Denise? N minus n and then 2 minus 1. What's the only thing going to be left?
1.
1. Mm-hmm. So good. So that means this -1 to the n plus 1 plus 1 divided by -1 to the n plus 1 just ends up being a -1 to the first part. And that's what I have right here. Is that part okay?
Yes.
Now, what else do we have? We have to deal with n plus 1 factorial divided by this n factorial. So it makes sense to put, you could do it visually and mentally in your head and reduce it, or rewrite it and write this in the numerator and this in the denominator, and then simplify that later on the next line. So that's what I wrote here. Is that okay?
Yes.
Now, what's the only thing left? It's the 1 times 3 times 5 all the way up to 2n plus 1 divided by 1 times 3 times 5 all the way up to 2n plus 1 times this extra n plus first term, 2n plus 3. So that's going right here. So that's this part. And underneath it is this part. Is that part okay, guys?
Yes.
Yes.
Now, what do you guys think? Should we take the limit yet or try to clean up some more?
Clean up more.
Because if we don't, we're still going to get infinity over infinity. We're going to get infinity over infinity here. This is not a problem, but matter of fact, well, I guess I didn't write it, but we could pull this out and write an absolute value of -1 by itself, and that would just be 1. So that's not going to contribute anymore to us figuring out what the determining value is of this limit question of the n plus first term divided by the nth term. So n plus 1 is larger than n. So take the larger expression and start to expand it out. And I hope we can I can write it down again. But Josh, how would we write n plus 1 factorial knowing that underneath it we have an n factorial and that we want to cancel out the n factorials? What can we do with n plus 1 factorial when we start to expand it out?
We could factor out one of the n factorials.
Well, it's like saying this. 4 factorial is like 4 times 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2 forever down to 1. What's n plus 1 factorial? It's the first factor, just like 4 was the first factor. N is the first factor, and then to get the next factor, you subtract 1. 4 minus 1 is 3. And the next factor after n would be 1 less, which is n minus 1, and so forth. So what's this going to be? It's going to be, what's the inside this factorial expression? It's what factor? N plus what?
1.
Times, what would be the next factor?
N plus 2. N minus 2.
It would be n plus 1 minus 1 more.
Okay.
And what is n plus 1 minus 1 more?
N.
N. So this would be n times, what would be the next one if we kept going?
N minus 1.
And you would keep going, wouldn't you?
Yes.
But what is this part right here, Joshua? What's this part right here equal to? N times n minus 1 times n minus 2 all the way down to 1. What is this part right here equal to?
N factorial.
Very good. And don't we have an n factorial on the bottom?
Yes.
So do you see how you would want to rewrite n plus 1 factorial over n factorial? The way to eliminate the factorial part of this ratio right here is to take the larger factorial expression. N plus 1 is larger than n. Keep the smaller factorial expression as is, because since this is larger, then when you keep writing the next factor, eventually you're going to get to the smaller one that's underneath, which means then you can divide everything out. But this quickly becomes the next factor here would be n, and then n times n minus 1 times n minus 2, but we don't have to write all that down because because all of this right here is the same as n factorial. And now we know the n factorials will divide out to 1. Is that okay, Josh?
Yes.
Brian or Denise, is that okay? Do you have any question on that?
No.
No.
Okay. So what's left over, Josh, when we have n plus 1 factorial over n factorial? What's still left?
n plus 1.
And isn't that progressing from something that was messy, that would give us problems trying to get the limiting determining value? Doesn't that now melt down or simplify down to something much less cumbersome or difficult?
Yes.
So that's the advantage of this ratio test, because when you do get to divide the n plus first term expression divided by the nth term expression, you're going to get a lot of this messy stuff dividing out, and then we're going to be left with something simpler. In some cases, it's still a lot of work. That was number 6. It was still a lot of work, even after we reduced whatever we could. But that's sort of an extreme question. This one, it does simplify fairly nicely. It's just that this little part right here, the 1 times 3 times 5 up to 2n plus 1, that can cause some people to be confused. Well, of course, anything can be potentially confusing. So the n plus 1 factorial over the n factorial can be confusing, but it's all relative, and if we practice these before, then we at least have a chance to get it again. We might need help, we might not, but anyway, I hope you understand that. So what happened to the -1 to the n plus 2 divided by the -1 to the n plus 1? We already showed that that was just -1 to the first power. N plus 1 factorial over n factorial is just left with n plus 1. Now what about all this part? 1 times 3 times 5 times up to 2n plus 1. Divided by 1 times 3 times 5 up to 2n plus 1 times one more additional factor, because that's the n plus first one, which means one more. And that's when we showed that the n plus first term would be 2 times n plus 1, which reduces to 2n plus 3. So here we are. Well, do we want to leave all these here and then try to take the limit? We still get infinity over infinity. So clearly these divide out. 1 times 1, 3 times 3, 5 times 5, and so forth, all the way up to the nth term, which is the 2n plus 1 part. So there's nothing left in the numerator except the 1, and divided by 2n plus 3. So that really simplifies all of that mess down into something fairly nice. Any questions there?
No.
So now we try to take the limit. Before we do that, I'm just going to extract this multiply -1 out and write absolute value of -1, which is just 1. You could wait. You don't have to do it yet. You could first put this together, take the limit, use L'Hopital's rule, and get whatever the determining value is times -1, then absolute value it, and that will be perfectly fine. Or just extract this out. I don't know what I did here. I guess I left it. No, for the moment I left it. So we went from this part and just put n plus 1 divided by 2n plus 3. The -1 I just left there for one more step. Could have taken it out already. It's just up to each individual, or you could leave it in all the way through, like I said. If we take the limit right now, what would happen right here? The -1's waiting, infinity plus 1 infinity, 2 times infinity plus 3 infinity. We would get infinity over infinity. which is friendly indeterminate. We could use L'Hopital's rule. In this case, it's probably quicker, a few seconds, not much. What's the derivative of n plus 1, Josh?
1,
And the derivative of 2n plus 3?
2,
So this would be 1/2 times -1 would be -1/2. The absolute value of -1/2 would be what, Josh?
1/2.
So that's one way. Or you could say, I want to, instead of using L'Hopital's, I'll divide everything by n to the first power, because that's the highest n value in the denominator, n to the first. And if you divide everything here by n, Brian, what's going to be the n divided by n?
Divided by 1.
1. And 1 over n, does that reduce yet? Or not yet? It only reduces when you take the limit. So for the moment, we'll just write what? And so n over n instead of L'Hopital's, you could do this, divide everything by n. And initially, when a person's learning this, they're like, well, that's a lot slower than L'Hopital's, because people might be already comfortable with taking simple derivatives. But once you do this a few times, this is also fast. And then sometimes you cannot use L'Hopital's rule. Oh, I take it back. You could use it, but you'd have to go through L'Hopital's several times before you're done. And then this would be faster. In this particular one case, it's like a tie, or L'Hopital's is maybe a few seconds faster, but there are other cases when this is a lot faster. So anyway, so what would we get here, Brian, when you divided every term by n? What would this become?
That'd be 1.
Plus
1 over n.
over
2.
plus,
3 over n.
and after a while you can even do that in your mind. Now take the limit, and that's where we are right. Any questions getting, and I pulled out this absolute value of -1. I just chose to. You could leave it inside. It's up to you. It doesn't matter. Either way, we'll get 1/2 at the end. So it's up to each person. I just took it out. Absolute value of -1 is this one. And now I'll take the limit, and we're going to get a determining value now. In this form, we're not going to have an indetermining value anymore. Okay? So 1 over infinity goes to 0. 3 over infinity goes to 0. So we get 1 plus 0, 2 plus 0, which is 1/2. Times the 1 is still 1/2. Here is the determining value of the limit that we've been trying to get. And now compare it to 1. And what happens, guys, when it's less than 1? Then we know the series what?
Converges.
Converges. The series converges by the ratio series test. It turned out I was just exploring myself, and this is an alternating series. You could actually use the alternating series test, and it's just quite abstract to figure out the limit formally. To show that it equals 0 is the first step. And then the second step, remember, for alternating series test is to show that each subsequent term is smaller or equal to the previous one. And that's, both of those are a little more abstract than using the ratio test. But you could, if a person wanted to, use the alternating series test with understanding that there's more abstraction involved. So even though this problem had its own abstraction by using the ratio test, it's still easier. I mean, it's an opinion, but it's still, in my opinion at least, it's easier than the abstractions using the alternating series test. Which is why the author said use the ratio test probably anyway. But, okay, any questions here, guys?
No.
So that's quite a bit to go through those two problems detailed as we did. But really, I don't know how else a person is going to understand it or have a chance to understand it unless we go very slowly in detail. And in the process, there's little pieces that may or may not need to be reviewed along the way. And that's why it takes so long. Okay. So now we go back to WebAssign. And this was number 7. Oh, and we have the ratio, the determining limiting value of our limit question using the ratio series test. The n plus first expression divided by the nth term expression did equal 1/2. That's correct. And therefore it converges. So those were the two that I felt was deservedly we should have waited for another moment, and that took its own hour plus and a half. Of course, if we were to do these again, we would not take an hour and a half. Maybe it would take 20 minutes or something, both of them together, if we were to go faster, yeah? But I was trying to give everyone a chance to understand all the minute details. Okay, so we have, of course, it wouldn't be right, I guess, if we didn't get tired on the last lecture day as well. So, so hang in there, and we're gonna go to 9.4, which I know is out of order compared to the author. But if you read in the end of the chapter of this author and other authors, when they put it all together with all these series tests, the last thing they suggest in their hierarchy of thinking is to use these tests as the last resort. And I feel the same way. I don't know why they don't put this section. I do know why. To prove the proofs behind the root test and the ratio series test, to prove why it works when you take the limit of the n plus first term divided by the nth term, the reason that proof, the reason it works and we can compare it to 1 and say diverges or converges, or it's inclusive, the reason that works involves a mathematical proof, and that mathematical proof requires us to use this limit comparison test that's in section 4. So that's the mathematical reason why authors put 9.4 ahead of 9.6. But in terms of practicality for Calculus 2 individuals learning these series tests, at least it's my opinion that this would be the last resort. But again, it's just an opinion. So, okay, so now I'm going to show you that. There are only 14 questions here. Now, maybe after we've learned everything else, this will not seem that difficult. And you're like, well, why didn't we do that already? But maybe that'll feel like that because we've already been practicing more things. And by the time we get back to 9.4. So anyway, so I'm going to show you, there's actually 2 tests right here, direct comparison test and limit comparison test. Of these 2 tests, in theory, only in theory does this direct comparison test end up being useful quite often. In actual homework problems, however, it's rarely needed at all. And so therefore, I'm only going to show you, I mean, if you want to do it on an office hour, I'm no problem, happy to show anyone, but I don't think it's that important in terms of the time we have and so forth, because you really would never need this except in theory. So anyway, so let's look at some problems here. There's 14 of them, and I just want to scan. And if my memory is correct, yeah, this, well, anyway. So there's a few problems. Well, I guess there's only one, but so let's not forget the things we've learned already. And also with all the perspective or the strategy, the hierarchy of thinking that we've been trying to practice. These last three questions are really just calculus 1 questions. So let's just take a look at any one of these first. I'm not going to do 12 and 14. You could easily do it yourself. If you put -4 in, you get -4 plus 4 is 0. -4 cubed is -64 plus 64 is 0. You get 0 over 0. So what happens when we take a limit and we substitute the limiting x value and we get 0 over 0, of course? What's that called?
Friendly indeterminate?
Good. And what can we do when it's friendly indeterminate?
L'Hopital's.
L'Hopital's rule, perfectly fine here. You could also divide all these terms by x to the what power?
X over x cubed.
Yep. So either one of those would give us a determining limiting value. We could also even, if it's factorable, this does turn out to be factorable, a sum of cubes. You could even factor this and then take the limit that way. And any of those 3 methods would be perfectly fine. So we'll just leave it at that. It's not a series question, it's just the limit question. Same with number 14. You substitute the -2 in and you'll get 0 over 0. And then you can either use L'Hopital's rule. You'd have to do it twice, but no big deal. You could divide everything by t, what?
Squared.
Squared, or you could factor, and if it didn't factor, then you wouldn't be able to use factoring, and then you would have to use L'Hopital's or dividing everything by t squared. But this also happens to factor. So there's really 3 simple ways to do those 2. So you guys can do that. This one right here is the one I feel is more worth mentioning in terms of offering to help. If we put -7 in, as it asks us to, 7 plus -7 is 0 in the denominator. Put a 1 over -7 and, put a -7 right there for x. You get 1 over -7. So that's 1/7 plus a -1/7, which is 0. You could use L'Hopital's rule. I'm just thinking myself what would happen. Yeah, so you could use L'Hopital's rule and you would get the answer. If we divided everything by x, I have to think about that. That will get us into, yeah, that'll be a problem. So we don't want to do that. So the only other thing you could do would be to put this together with a common denominator on top and then simplify. So either L'Hopital's rule or simplify this algebraically. You can't factor it, but we could get a common denominator here. So I'm just going to show you that real quickly before I show you the last thing. So in the denominator, we would still have this right here, 7 plus x. This is not a sequence formula. It could be, and we could end up having to take a limit, and that would be the question. But these are just 3 problems I put in here to practice limits still, and kind of put it back into a Calculus 1 perspective as well. Anyway, on the numerator, the common denominator would be 7x. And what's this denominator right here? Denise missing 1/7 and 1 over x. The common denominator would be these two, 7x. So what's missing on this denominator? The 7.
X.
X. So if you multiply the bottom by x, you multiply the numerator by x. And what's 1 times x, of course? It'll just be what?
X.
Good. And then the other fact and the other piece, what's missing on this x with this denominator of just a factor of x? It's missing what to have a common denominator? It's missing a
7.
Times the top by 7 as well to make the correct adjustment. And we get what up here then, Denise?
7.
Then this could if we took the limit still right now, we would get -7 plus 7 is 0 divided by, this would be 7 times -7 is -49. You would get 0 over -49. Oops. Over 7 plus -7 would be 0 still. And you would still have, and this part is 0, you would still have 0 over 0, and that would be still a friendly indeterminate. And I don't think you want to take the derivative of this, which would be quotient rule. The derivative of this part is simple enough. It's just 1, but because we can do better than that and be more efficient than that. So what we do is take the 7 plus x, leave it for the moment. Oh, it depends how you want to say it, sorry. Take, put a 1 underneath this. We have fraction divided by fraction. And we could rewrite this as x plus 7 over 7x times the reciprocal. I should have put this in light green, sorry. Times the reciprocal of this, which would just be 1 over 7 plus x. But 7 plus x is the same as x plus 7. These are the same. They're multiplied factors, so they are 1's in the numerator divided by 1 in the denominator, so that divides out to 1. So now 1 times 1 is 1. And we have 1 over 7x. And now if we take the limit, have we manipulated this enough so that we no longer will get an indeterminate value, but a determining value. So 1 over 7 times -7, and of course, is -149 over 1 over negative 49, and that is a determining value. So we would be done. And that's what's right here, okay? Any questions here?
No.
So that's just a little bit of review of some limits there. So I just threw that in there because these above here, which we can use the limit comparison test, or maybe we don't even have to get that far. If we take the limit of the individual terms and we get anything, excuse me, not equal to 0, well, then we already are done by the nth term test for divergence. But so here we go. So let's see here. Let me look for a nice problem I think is friendlier to start with, so it doesn't look so intimidating. Okay, so number 1 looks good, or number 8 looks good. So how about number 8? So we have this series right here with a formula of 1 over n cubed minus 27. So I'm just going to write that down on my notebook. I don't think I wrote any of these down. Maybe, but no. So anyway, okay, so let's look at number 8 in our last section. Unfortunately, I wish we had another 2 weeks or something, but we don't. So, but I think anyone that wishes to take Calculus 3, you're going to be, if you've done well here and understand things, you're going to be fine in terms of background information. Of course, there's still going to be new challenges and new things to learn, but your calculus foundation is solid where you will be fine. I hope. Okay, well, I believe so. That's how I've had to teach this class this way many times, and many people come back and said they were fine for Calculus 3. But anyway, it doesn't mean that the last sections we didn't get to are not interesting and not worthwhile, because they are, especially the next couple. I really wish we could have gotten there in terms of interest, curiosity. But anyway, so number 8. And we have this formula right here. And it is my battery doesn't die here. Okay. So we have 1 over n cubed minus 27. And so here is the last series test that we will cover. Now, if we take the limit right away and hope that we could use the nth term test for divergence, it won't get us very far, because what happens, of course, when we put infinity into this equation of the formula of the sequence, we would get infinity cubed minus 27, which is infinity minus 27. So 1 over a larger and larger number converges to what?
0.
0. Which means this series, when you start adding up the individual terms of this sequence, it still is possible. Well, this is the case. The only case a sequence's terms, when you add them up forever and ever and ever, has any chance at all of converging to a single finite numerical sum value is when the individual terms themselves are getting smaller and smaller, closer and closer to 0. And that is what's happening. So therefore, we know that this sequence when you look at the sum of the infinite terms, it does have a chance of converging, which means we need to do further exploration. This is not trying to put all the series tests back in our minds. This is not geometric. It is, you would not be able to integrate this 1 over n if you put x cubed instead. You would not be able to integrate this because if you tried, none of the things would work, including renaming. If you put w equals x cubed minus 27 in your mind or on your paper, the derivative of that would be 3x squared, and there is no x squared on the top, so we would not be able to integrate it. There's no square roots where we could try to use trigonometric substitution or anything of that nature, partial fraction, decomposition. Maybe we could factor this down. Oh, but when you factor it, you don't get the right irreducible quadratic, so that would not work. But anyway, so you can see how you could go through lots of things. This may have to think about it for a second. If we tried to use the ratio test, we would get, when is the ratio test fail, guys?
When it's equal to 1.
Yeah, if we use the ratio test right here and we wrote it out and we took the limit, we would very quickly get the limit, the determining value, and it would equal 1. And then we would be bummed out and we would have to go use another test anyway. And the same, oh, well, not the same, but the root test would not clean up, because if you took the nth root of this, you wouldn't be able to do anything with it. And so that wouldn't help either. sorry, guys. Can you guys hear me?
Yes.
Okay. You know, you might be wondering why don't I just have my phone plugged in to the charger, but there's sometimes I have issues when I don't have my phone connected to my desktop computer and I have connection problems or it's slow, freezes. So that's why, but I hope it doesn't do that here in what we have left. Okay, and there isn't that much left, okay? So hang in there. And so we were saying here, we cannot use the ratio test. This is very similar to just 1 over n cubed. Or let me write it this way. A sub n equal to 1 over n cubed. And what kind of series or sequence is this, guys, when you have 1 over n to a p power?
P series.
P series, good. But it's not where you have like a 3 or a 2 on the top and you can factor it out in front. And so because we have the minus 27 is right here, it's not like a factor, it's not times 27 where you could take it out or something. So we cannot, we can't just use the P series exactly right here because it's not precisely the exact form of a P series, which is this. It has something extra. So, but it still behaves very closely to a P series. So what we can do, everyone, is we cannot use geometric. We cannot integrate this. I mean, sometimes there's overlap. You might be able to come up with something clever to integrate it and use the integral series test, but I don't think it's really worth going that route because this works out very nice. It's not a P series, but it's close to a P series. And so that kind of gives us a clue to try this comparison test and compare it with this P series. The limit comparison test is you pick up another simpler sequence formula that you know something about, and usually it's going to be P series or geometric, those two usually, and we're going to compare the sequence that we have and compare it most of the time, the vast majority, to the P series or the geometric that this looks very, very close to. So it's like, this is like a relative of 1 over n cubed. You cannot say it's precisely a P series, but it's very close to being a P series. And so let's try to use and compare the P series, which is very easy to know. We know very quickly if this is converging or diverging P series. And remember, if we look at our notes, the P series, remember, if P is greater than 1, and versus if P is, and by the way, P has to be a positive number, a positive real number. So if you have 1 over n to the p power, where p is a positive real number, can't be negative, can't be 0. I mean, if it was 0 anyway, it would be a really simple problem because you would just have 1. But anyway, I guess technically it could be 0. Okay, it would just diverge. But so I guess that's why they write here, if p is less or equal to 1 and greater or equal to 0. I'm trying to remember if they write it that way or just say less or equal to 1. I can check real quick. Yeah, they don't bother to write greater or equal. They could. It's just that it reduces down to a very simple question, and they don't bother. So, so either way. But this is when it converges. If p is greater than 1, it converges. The series converges. And if it's anywhere from 0 to 1, and the only reason they don't put equal to 0, because if this was 0, what's n to the 0 power, guys?
1.
1, and you would get 1 over 1, which means every single term is 1. And then technically, you might say it's not a p-series anymore. It's just a sequence where every term is 1. And that's not very exciting because do these terms, are they getting closer and closer and closer to 0, or are they staying at 1?
Staying at 1.
And so therefore, if you start to add these up, is there any way when you add up 1 plus 1 plus 1 plus 1 forever, it's going to converge closer and closer to a single sum, a finite number, or will it just keep getting bigger?
It'll keep getting bigger.
Yeah, so then this would diverge. So, so if it did turn out to be n to the 0, it wouldn't be very interesting, and they probably will never even ask that. But if they did, it would diverge. Okay. So anyway, if p is less or equal to 1 or greater than 0, then the series diverges. And that's the p-series test. The p-series test. So what we do is the following. This is not an alternating series. You couldn't use the alternating series test. You cannot use, if you tried the ratio series test, you would get the limiting value to be 1 and the test would fail. It's always going to fail if this is like a relative to a p-series, or even if it is a p-series. The ratio test will always fail in that case. So that's why we are not going to use the ratio series test. The root series test would not be effective because to be effective on the root series test, you need the exponent to be an n. And when you take the nth root of something to the nth power, then they compose out and you have an easier expression to deal with. And that's when the root series test is effective. So this is not the only one that would be possibly have a chance would be the integral series test, but if we did, it may or may not work. I'm not 100% sure. And if we did, it would be nasty. So I don't think we want to do that. So what we do, everyone, is say, hey, this looks very, very similar to this p-series right here, where p is equal to 3. And when p equals 3 on a p-series, it converges. And so we are going, so soon as you know what this is a relative of a simple p-series or a geometric sequence, then you're normally going to go to this comparison series test. There are 2 of them. One is direct, one is limit. The limit one will almost always be fine at this class level. And so I'm only showing you that one. Okay, unless you want to ask me like an office hour. We are going to compare our sequence to what we realize is a very close p-series that converges. So once we set up this first discussion, the problems work out very nicely and quickly. That converges because p is equal to 3, which is greater than 1 from the p-series test. That doesn't mean we're done. That just means we're stating, hey, this is the comparison. This is what we're going to use to compare our sequence. And because we know what this one does, it converges very quickly by just looking at the p-series test value, then we know this converges, and so we have one more step to go to see if this converges or not. That one extra step that we're about to do, it could be to compare it in terms of an inequality, which would be the direct series test, direct comparison test, or as a limit. The limit just is by and large easier to do than the inequality comparison, generally speaking. So that's why I'm going to do that. So let's compare and it seems like we're doing the ratio series test, but we're not, because it's a different ratio. Let's compare the ratio, not this ratio, not this one. No. That would not be picking another series. That's just what we've been learning, which is to write the n plus first expression down of the sequence that is given to us and dividing it by the nth term expression of the sequence, which is this, and then taking the limit and comparing it to 1. That's what we were working on the last couple, however long we've been here today and last Monday. Not this ratio. It is a ratio, but it's not the ratio we're going to use. It's a different ratio. 2/3 is a ratio. 5/7 is a ratio. They're not the same ratio. And the same idea here. This is a ratio, but it's not the ratio we're going to use when we look at the comparison test. We're going to look at the following ratio. And we're going to look at the original sequence compared to the one we picked, the extra sequence that we feel is closely related to the given original sequence and whose convergence or divergence is readily known. Usually a p-series geometric those kind. Instead of writing this in all these words, we can say, or mathematically, so I'm kind of going in the reverse order here, from right to left, or if we write this one as, it doesn't really matter how we call it, let's say this is the original, A sub n. The extra sequence that we come up with ourselves that, hey, we think, hey, this looks really close to this p-series, 1 over n cubed, whose convergence and or divergence is readily known. Readily meaning, oh, p equals 3, p is greater than 1, so it converges by the p-series test. This one we came up with, its convergence or divergence was readily found. And yeah, and so that's why, if not all of them, I can't remember for sure, but the vast majority will be, these will be similar to either a p-series or a geometry. Okay, so let's say we call this one C sub n, because this is the one that we found ourselves. This is the one we find. Sequence we find in our mind, so to speak. We find in our minds to compare, that we will use, that compares. I feel like I'm being redundant here. That compares with A sub n. Forgive my terrible sentence here. Anyway, so here we're going to put A sub n over C sub n. Technically, if anyone wanted to, they could say, I want to compare the other way around, and you could also do it this way, C sub n over A sub n. This is the original. This is the one we came up with in our minds. This would also work. Some authors write it this way, and some authors write it this way. Some authors write it both ways and say you pick. And that sounds kind of bizarre, but it's because all we have to do now is take this ratio, take the limit of it, we surely use limits a lot in this chapter, you know, and we, if we get so when we take a limit, we always, when we take a limit, we want to get the determining value. Sometimes it's very quick. Sometimes the determining value takes a lot of work, like the first problem we did today, number 6. To get the determining value, it took us a lot of work. Sometimes you get it right away, and you don't even have an indeterminate of any kind. Doesn't require any cleverness in terms of changing it from unfriendly to friendly and so forth. But what are the possible determining values? We could get infinity. Oh, we can get a finite
Numerical
single value, good. Which means the limit what?
converges.
Converges. This is when it converges. If we get this, when we take this limit, and once we get the determining value, if it's a finite single value or number that is positive, I'm sort of getting mixed up here in my, I'm sorry. Let me first say this. What is a determining value when you take any limit? Well, 1, you get a finite single value, and that's when the limit converges. Or we can say the limit exists. The other 3 possibilities are infinity only, negative infinity only, or oscillating. In all 3 of these cases is when the limit what? Yeah, if you get any one of these, the limit what?
Diverges.
Diverges. So, when we use the limit comparison test, that means we're going to find in our minds another formula of a sequence that is very close to this one. And usually it'll be a p-series or geometric. And we know that this one we pick, we'll know if it converges or diverges very readily. And then we say, okay, now I'm going to take the limit of the original sequence in the numerator, the one we came up with to compare in the denominator. If you want to reciprocate it, that's fine. It'll still work here. If you get a limit of 4/3 this way, you'll get a limit of 3/4 this way instead, and you'll still be the same result. I don't know if I want to go over all the possibilities here. I'm just going to ask you to believe me. Okay, so okay, so if we take the limit right now, if we get this, this, or this, then I just lost my thought. Then if we get any of these, then we don't know, let me think, we don't, I'm not sure, I gotta think about that. If we get this one though, a finite single number that's positive, it has to be positive. If that's what we get, any positive finite number, then the series, the sequence that we were given to start with will do the exact same thing as the one we came up with in our mind. This one that we came up with in our mind was a p-series which converges. So if we take the limit right now of this, if we get a finite single value that is positive, then the sequence that we were given will converge because the one that we compared it to converged. if the one that we compare it with diverges, and we take the limit and we get a positive single finite number, then the one we were given will diverge as well. And the reason my mind pauses here is because I don't think, I have to think about it for a second, but I don't think this will come up ever, but let me reserve my thoughts on that for a moment, okay? Okay, so anyway, if the limit as n approaches infinity of the ratio of the original sequence's formula or expression divided by the one we came up with, if we take the limit and we get a positive finite value, which means it's going to converge, but specifically not to any finite single number, but with one more condition, positive finite single value. Then our given sequence or our given series A sub n will converge or diverge as C sub n does. Whatever C sub n does, then A sub n will do the same thing. We could get into kind of a lengthy discussion about why this works. I don't think it's the best moment to do so. I think we should practice a few problems, and then maybe it'll be a better moment to explain why this idea works. So let's go to number 8. And this is a case where it takes a long time to sort of explain it, but to actually do the problem is very quick. So number 8 again, just rewriting it here. I don't know if I wrote it wrong or it did say start at n equals 4, which kind of surprises me, but they're just, I don't know, I don't think there may be a very good reason for that. I'm not positive. Have to look at the individual terms, but I'm not 100% sure. But anyway, it doesn't matter for us. We're just going to do it. So here we would look at all the terms forever, but starting at n equals 4 is all. N equals 5 and so forth. Oh, probably because I guess I answered my own question. Because at 3 cubed would be 27. 27 minus 27 would be 0. That would be undefined. And so that can't happen. And if you put a 2 in, 2 cubed is 8. 8 minus 27 is a negative number. And we need these terms to be positive terms. So, yeah. So this formula only works when A sub n and C sub n's terms are positive. All of them have to be positive terms. So that is a condition. I'm sorry, like I said, I had to think about that. Okay. Then we can try to use this limit series comparison test. Okay, so finally, let's do it. So so this is our A sub n, the original given one. What one did we decide is looks like this is this original one they gave us to analyze looks like it's a relative similar to what? Simple sequence formula that we easily know what it is and also can readily decide if it's convergent or divergent. And that is the P series what? 1 over what?
N to the P.
N to the P, and what specific P value for this one?
3.
Which is P equal to 3, which is greater than 1, which means converges. P series. So take the, now we're going to try and use the limit series, the limit comparison series test. Which is to take the limit as n approaches infinity of A sub n over C sub n and our A sub n is the given original one, 1 over n cubed minus 27. The one that we said that, hey, this 1 over n cubed minus 27 is very, very close to the P series 1 over n cubed. And now we take this limit, just like we go now and take any limit, and we try to get the determining value found by whatever means we've learned thus far. If we just plug infinity right away, that's what you would do first always. Well, what would happen? 1 over infinity cubed, that would get closer to what, guys?
0.
Infinity cubed minus 27 would still be infinity. 1 over infinity would still be 0. And this is a friendly indeterminate. You hanging in there, Denise?
Yeah.
Okay, and now that's indeterminate. We could try to use L'Hopital's rule. I don't think that's the best idea yet because we can simplify this rather easily. 1 over, we can change it from division to multiplication. And I hope our practice and our intuition tells us that that seems more likely to clean things up. So we would have 1 over n cubed. This is not an absolute value. It's a grouping symbol. N cubed minus 27 times n cubed over 1. Well, we've just rearranged this expression of A sub n over C sub n, trying to get rid of the friendly indeterminate, which was a 0 over 0. Unfortunately, now we have, if we take the limit now, we get infinity cubed, which is infinity times 1 is infinity over infinity, and we have a friendly indeterminate again. Yeah, it's just not 0 over 0, it's infinity over infinity. So then either we back up and try to do something else, or we take this and try to clean it up some more, manipulate it some more. And if we put it as did you guys hear me in the last several seconds?
No, it froze.
It froze. My phone was ringing and I never had this happen before, at least I don't remember. And when someone's trying to call me, I guess everything freezes. Because my phone, again, is my camera and my microphone. Anyway, I'm gonna have to break down and buy something else, I guess. If we write it from here to here, we still get infinity over infinity, so that didn't help a lot. We could use L'Hopital's rule, or we could divide everything by n, what, guys? N
Cubed.
cubed, either one. Either one will work. Denise, what do you want to do there?
Divide everything by n cubed.
Okay. So can we do that on our mind here? And what would happen if we take n cubed divided by n cubed? What would that be?
1.
Good. In the bottom?
1 plus 27 over n cubed.
Good.
Minus
Mhm.
27.
And that's fairly quick to do. And the derivative would be nice here, and it would, both would work out nicely. And now what happens if we take the limit? We are not going to get an indeterminate anymore, or a friendly indeterminate anymore, and we're going to get a determining value. Yeah, and that determining value, again, just like any other limit question, is either this kind or one of these three kind that are diverging or limit doesn't exist. This is converging, the limit does exist. But for our purposes, we're not only interested in the limit converging to a finite single number, but it has to be a positive finite single value. And so let's see what happens. What happens here then, Denise? We get 1 over 1 minus 27 over infinity cubed. We'll get closer and closer to what?
0.
And so what do we get?
1.
1. And we don't panic and say, oh, that means the test fails. That was the ratio series test or the root series test. But on the limit comparison series test, we get 1. That is a determining value. It's a single finite number, but more importantly, it's what kind of single finite number?
Positive.
Positive. So this is the determining limit value, and which is finite positive single value. It's kind of being redundant saying single value, because when we say a finite positive number, we're saying that it means a single one, but just to emphasize. Therefore, this series, and we wouldn't have to write it down like this. We could just say our series or a sub n or whatever. But this is this one we were being originally asked about. It's going to do whatever our C sub n did. Yeah, and what did our C sub n do, guys? What did our C sub n do? The one we came up with is 1 over n cubed. It what?
It converged.
And so this one also converges. By the limit comparison series test. Any questions there?
No.
So it took us a while to actually do the problem, but you can see the problem is in itself is fairly short. So let's try, well, let's go back to WebAssign. That was number 8. It does converge. Identify which test you used. There's more than one correct answer, but you only need to select one. So yeah, which one, let's just put it this way. Which one did we use?
Limit comparison.
Yeah. We could have also used this one. It may or may not have been possible to do the integral. I would have to explore it. We could not use this one because we didn't get the limit of this formula of the individual terms did not equal 0. So we couldn't just stop there and say it diverges by the nth term test for divergence. I don't know why they didn't write it all out. It's not geometric. It's not exactly a p-series. This telescoping, I don't really want to talk about it here. It is a very, very unique kind of thing. You're not going to be responsible for this, and so I'm just going to leave it as that. You're not going to have to know that one. It is, again, if we had all kinds of hours as well, I would be happy to show what that is. But I know that we can do this problem much more efficiently than using this right here. So this series test is not very efficient in terms of compared to the other tests that will work anyway. So that's why I'm choosing as your teacher not to show you this one. And it's not out of laziness or anything. I just know we don't need it because we can easily use the limit comparison test instead on this case. So I'll just leave it at that. Okay. Let's try number, let's see. Number 9. Theory, well, the summation, oh, they don't give us in summation form. It's just a habit. No, I just looked at it. So I'll write down 1 over 900 is the first term, or whatever term we want to call it. The next term is 1 over 1800, and so forth. So the first part of this question, just like we've had in other assignments, is to figure out the pattern and of these terms, just like this one here, and before we can begin. So that's the extra little caveat there of seeing if we can figure out what the pattern is. Okay, same as this one down here. Okay, so let's go. So trying to discover the pattern here. Well, all of these terms are fractions. So ours, the formula is going to have to be a fraction. And all of the numerators are 1 all the time, so that makes the numerator easy to figure out. And then from there, well, now comes, it takes some creativity here, of course. So let's see. So my mind went a little bit blank there, trying to see the pattern right away, but so I had to concentrate a little more on myself. Okay. So I see this. All of them have a 1 in the numerator. All of them have 100. That's what I initially saw. But then I also saw it's times 9, because 9 times 100 is 900. This is 100 as well, times 9, which is 900, but then times 2 gives you 1800. And so on. 100 times 9 is 900, times 3 is the 2700, and the same here. So any questions on that observation?
No.
No.
So instead of writing 100 times 9, oh, by the way, you could always say times 1 here. And therefore you have a 1, a 2, a 3, a 4. That's the only part that's changing. The numerator is not changing. The 100 is not changing. The times 9 is even not changing. Therefore, if we write out these terms forever, and we want to get the general formula for the nth term, then we could say right here or down here, and we could write it here already, or write it here and then move and then write it in this form, either one. But we notice that there's a 1 all the time. There's a 9, 100 times 9 all the time, but you can just put that back together and write 900, so you don't have as many objects here as we don't want to complicate it unnecessarily. So 900 is the same all the time, and then it's just the next piece is the part that's changing all the time, from 1 to 2 to 3 to 4 to 5 and so forth. So if we call, so then it would be convenient to start at n equals 1 and n equals 2 and so forth. Therefore, what would be right here then, class, in excuse me.
N plus 1.
Okay, almost. So if we put n plus 1, you would be right, Joshua, if we decided to start at n equals 0 instead. Because what would happen if you put 0 plus 1 here? What's 0 plus?
It would be 1.
And then 1 times 900, 1 times 900 would give you the 900, wouldn't it?
Yeah.
And if we put n equals 1 here, and so n equals 0 and n equals 1 and so forth, if you put 1 here now, what would be 1 plus 1?
2.
Times 900.
1800.
And then your formula is absolutely correct. Yeah?
Yes.
Now, what if, not to try to say there's anything wrong with your formula, because we could use it. And when we then look at this formula, we would have to then figure out if you took the limit of this right off the bat of the individual terms of the sequence, you would get 1 over infinity, which converges to 0. That means there's a chance that this series can converge, and we would have to proceed by using one of our series tests, and then we would go through the whole hierarchy, and it's not geometric. This is integrable. You could use the integral series test. So that would be possible. It's not a p-series. You can't use a p-series. It's not alternating. There's no -1 to a power there. It's not alternating. So we cannot use the alternating series test. It's if we tried to use the ratio test, this is kind of like a p-series n to the first power. That would end up giving us equal to 1, and the test would fail if you tried it out. And then if you took the root test, there is no nth power, so the root test would not help this at all. So now we go back and we can either use the integral series test or try a comparison test and come up with another sequence formula that is similar to this one. So we certainly can do that, or let me just throw this at you, and then I'll still pick yours because you picked it. But I also just want to show you what would happen if we would have instead started at n equals 1 instead. Well, then our formula would have been a sub n equals 1 over 900 times. And then what would happen, Josh, if we would have picked n equals 1 first? Then we wouldn't have had to write n plus 1. We would have only had to write times what here?
1.
Well, you're right. It would be 1 when n equals 1.
Oh, just n?
Mm-hmm. And you see how close this formula and this formula is?
Yes.
Either one will work when we end up trying to use any of the series test. And it would turn out you could either use the integral series test with this one, just like you would use with this one, or we can use the limit comparison test and come up with another function, another sequence that looks very similar to this one or similar to this one. My only extra thought on that is, if you asked 1,000 people, find another sequence formula that's very similar to this and this one, maybe people are more likely to see one that's related to this one faster than this one. But that's all. But it's very, very slight. What formula can you guys think of that would be very close to this one?
P-series?
Go ahead.
P-series?
P-series, good. And which one?
What do you mean, which one?
So what would I, and I don't want to write A sub n, I want to write C sub n. What formula can we make up on our own? And you said a P-series, that's almost, is very, very close to this one. That's less complex.
900 to the nth power?
Well, if we write 900 to the nth power, now we're looking at a geometric. Is this to the nth power, Josh, or times n?
times n.
Yeah. So, yeah. So not that one. Denise, do you have an idea?
I thought you said it wasn't a P series, and now it is.
This one is not a P series, but it's very close to being a P series. What
How? I don't see that. Like, that's not my first thought.
What happens if you have anything like this? 1 over n to the P power.
Yeah, then the P series.
That's a P series. What power? What what is the value of P on this one? 1 over n.
1.
1. So if we compare it to 1 over n to the first, isn't this formula that they gave us? Well, we had to figure it out. Isn't this very close to this one? It's just that we don't have the 900 right here.
Mm-hmm.
So this is a very close, this right here, the one they gave us, is very close to this one, isn't it?
Yes.
Is that okay, Denise?
Yeah.
See, this is the old, if there's something that is abstract about this comparison, limit comparison series test, it's this part right here that we're thinking at this moment. It's coming up with something that we have and finding one that is similar to the one in front of us that we know that we can figure out if it converges or diverges. That's the creative part of this test. And that's the reason I wait until we've done all the other ones, because I think we're more likely to catch on a little bit quicker after some more practice and experience. So I hope you do agree, Denise, that 1 over n to any positive value right here is a P series, yeah?
Mm-hmm.
And including P equals 1. And isn't there a 1 right here on this exponent?
Yeah.
And this is just a multiplied number in front of it.
Mm-hmm.
So 1 over 900 times n to the first power, that's very, very similar, close, related, like just 1 over n to the first power. And you're like, what does it mean to be like, to be similar? Yeah, well, if we ask you this, x and 2x, aren't they kind of similar? Whatever that means, kind of, yeah? And maybe that's the hard part. What does it mean to be similar? If you had 1 over n squared, isn't that a P series, Denise?
Yes.
And what's P equal right here?
2.
So if we have this, and you're like, oh, and even if there was a number on top, you could factor that out. You just can't take these out. But you could say to yourself, or we need to be able to say to ourselves, hey, I have 1 over n squared, and I know that's and I know 1 over n squared is a P series. And so this is not precisely a P series, but it's closely, it's similar, and that's the problem. What does similar mean? But instead of a times 1, we have a times what?
3.
Instead of a plus 0, which down here doesn't do anything, we have a plus what?
4.
That's what we have to say to ourselves. Yeah, this is not precisely a P series, because to be a P series with the n squared, it has to be just this. But the times 3 is not a big change to n squared, and neither is adding 4. Does that kind of make sense?
Mm-hmm.
If we look at the graph, and 1 over 3n squared plus 4, sorry, what was I going to say here? Well, anyway, here are those terms of this sequence, those individual terms. If we now instead type, and I'm missing something that I wanted. I'm sorry, I forgot to type something. My mind was frozen there. And I want to do this instead. So I'm sorry, my mind is forgetting something here. Oh, I know. I wanted to show you all the points. So sorry. No. I'll get there. I apologize, I'm forgetting how to do this, or I show all the points, but here are the individual points of the sequence. You can see they are getting closer and closer to 0. Can you see that okay?
Yes.
And that's like the 14th term, the 15th, and so forth. Now, and I hope my mind will remember, I'm sorry, but anyway, here's the other formula, which was the one that's closely related, 1 over n squared And if we look, so where am I? Oh, so here is the 1 over n squared p series that's similar to this one. So when we mean similar, yeah, they start out, the first term, they're kind of far apart. But what happens very quickly, don't they have a very similar situation going on here as you go out further? Yeah,
Yes.
okay. And that's because the only difference between these two is this only has a 1n squared, this has a times 3, and that does have somewhat of an impact. And the plus 4 also has an impact, but it's not a very large impact. And as you can see, yeah, it only makes a little bit of difference at the beginning, but after that, and look at these numbers are not very far apart. I mean, this is not even 0.1 and 0.3, so these are actually very close together. I have it scaled so that you can see the difference. So I hope you can agree that these are similar to each other.
Yes.
Yeah? Okay. And that's what I mean by similar. 1 over 3n squared plus 4 is very, very similar to 1 over n squared. It's just that this has a times 3, that this one only has a times 1. This has a plus 4, and this one has a plus 0, which you don't see. And so therefore, this is very closely related to this one. And this is a p-series, and we know we can figure out the convergence or divergence of this p-series very easily. Does that make sense?
Yeah.
So I'm going to go back to we lost. I understand. It's taking forever. He has to go. Okay. Go to work. So, okay, so we're almost there. And so what is a nice formula to come up with, Denise, that is fairly closely related to this one? Yeah, it's a p-series, and the giveaway is n to the first power. So so we're going to say just 1 over what?
N to the first.
Yeah, and if you said 1 over 900 n to the first, well, that would be not similar. That would be exactly the same as that, right? Okay. And do we know, can we readily determine, can we quickly or readily determine if this sequence that we came up with converges or diverges? Well, it's a p-series.
Yes.
And what power?
1.
And that means this series what?
Diverges.
Good. So what are we going to try to do right now? Take the limit. So we're going to try using the limit comparison test. We could also use a different comparison test, the one with inequalities, and that is the direct. I just feel this one works out cleaner in most situations and less abstract. So can you help me out here, Denise? What are we going to compare? What ratio? The limit as n approaches infinity, and don't say a sub n plus 1 over a sub n. That would be the ratio series test.
It's going to be a sub n over c sub n.
Good. So what are we going to write for a sub n?
1 over 900n over 1 over n.
Do you see how simple that's going to be to simplify?
Yeah.
And then we're going to be able to take the limit with virtually no issue. Yeah.
Yes.
All we hope for is that we get what? When we get the determining limiting value, we hope it's what kind of determining value?
A single finite numerical value.
Very good. And not only a single finite numerical value, but what kind of single finite numerical value?
Positive.
Does that make sense?
Yes.
And if we do get the single finite positive value, then what are we going to be able to say by the results of the limit comparison series test? That our sequence they gave us, when you add up the terms forever, that sum of those terms forever will do the same thing that the one we picked ourselves, that is very closely related to the original one.
Okay.
And what does this one do?
Diverges.
And so this one will also what?
Diverge.
As long as we take the limit and the determining value is a positive finite, a single positive finite number.
Yes.
And you might be thinking it seems kind of magical, and you might say, well, what if I would have picked n squared and I would have still got a single finite positive number, and n squared is a converging one, and then you would say, oh, well, this one converges also. But if you did pick 1 over n squared, Denise, and you took the limit here, you would not get a single finite number. Because if this was an n squared, just pretend, and then that would be what up here, p equals 2.
Mm-hmm.
And what happens when p equals 2?
It converges.
And what would happen if we did that with this one?
They would converge.
Well, we better not, because we can't pick one sequence formula and then put it in this test and then get a single finite positive number, and then we'll say, oh, the one they gave us converges. And then if you pick another one, 1 over n to the first, and that diverges, and you do the limit with that one, and you get a single finite positive number, and then you'll say this one diverges. Well, you can't get both. This one either converges or what? The one they gave us. It either converges or what?
Diverges.
So if we pick a different one up here as our c sub n, and if we pick 1 over n squared, let's see what happens. So how would we clean this up, Denise, if we have this over this?
You can put, I'm skipping over some steps that I already did, and I went straight to n over 900n.
Oh, this is without the n squared, right?
Yeah.
Okay. So you would get, what'd you say, n over 900n?
Yes.
Good. What would have happened, Denise, if we would have picked c sub n to be 1 over n squared, which is p equals 2, which is converging p series? What would have happened when we took, instead, we would have picked this one. Then we would have got limit as n approaches infinity of, what would we have in here instead, Denise?
We would have 1 over 900n over 1 over n squared.
And then what would happen when we clean that up?
There would be n squared over 900n.
Good. And that looks very close to this one, huh?
Yeah.
And let's keep going now and see what happens.
Okay.
And what about the one up here you picked? Or we picked together? What happens when you take the limit right now? You would get infinity over,
Infinity.
so that's friendly indeterminate.
Mm-hmm.
Either use L'Hopital's or divide both of these terms by what?
N.
Either one. Both are real simple. And what would happen? What do you want to do?
I got 1 over 900.
Good. Or you could just divide them out for that matter.
Yeah.
And what is the limit of 1 over 900 as n approaches infinity? Is there any n left in here to take the limit of?
No.
And so what would we get?
1 over 900, which is less than 1,
It
but
is
greater than 0.
It's less than 1 and greater than 0. That is correct. But what is the limit comparison series test? All we need is our determining value to be what?
Positive.
And finite, which is a single positive finite value. And what does that mean then, Denise? Thus,
Our series diverges.
our series does whatever the one we came up with does, correct? And that one diverged, so we would say, I just ran out of space here, but therefore, our series must also diverge as C sub n did by the limit comparison series test. Is that okay?
Yes.
Now, here comes the part that typically will confuse us when we're learning these things. And you're like, well, what if I would have picked 1 over n squared instead? Yeah?
But why do we pick 1 over n squared?
Yeah, why would we? Because I like really even more distant relatives. I don't really like my closer relatives. So I'm going to say that 1 over n to the first is kind of like 1 over n squared.
Mm-hmm.
I'm sorry, let me take that back. I say that 1 over 900 times n to the first is kind of like 1 over n squared. Not that different. Instead of times 1, instead of times 900, it's times 1. There's no here plus anything. There's nothing here. Instead of n to the first, that's an n squared. I think that's pretty close. It's only 1 apart.
Mm-hmm.
And so somebody might think that way. So what I'm trying to point out is, what happens if we did? Well, something better fall apart here, because we already know from up here that this sequence, when you add up the terms forever, is going to have to do what? It's going to have to what?
Diverge.
Diverge. So if we pick this one instead, we better not take this limit and get a single positive finite number and then say, oh, our original sequence, when you add up the terms, converges because this one does. And something better happen right here. We better not get what kind of determining value when we take this limit?
A positive.
A positive what?
Single finite value.
So what else could we get if we don't get a single positive finite number as our determining limiting value? What else would be possible?
Infinity, negative infinity, or oscillating.
Mhm. Or even a negative number.
Mhm.
A negative single finite number. Or
Okay.
a zero finite number. You understand? So
Yes.
if we pick the wrong one, so let's keep going. And what would happen if we put infinity in this now? We would get
It'd be
infinity squared over
over
9.
infinity.
So we would get infinity over infinity. Is that determining the value yet or indeterminate?
Indeterminate.
And what kind of indeterminate?
Friendly.
And what do we do with that?
Divide everything by n.
Good. And we can write it down or do it mentally. What's going to happen when we take, okay, I'll write it down, n squared 900n, divide everything by n.
Mhm.
What are we going to get?
We're gonna get n over 900.
Very good. And what happens when you take the limit now?
It's infinity.
And is it infinity over infinity, indeterminate, friendly indeterminate, or is it just a single infinity only?
It's just an infinity only.
What does that mean?
That means that it diverges.
What diverges?
C sub n.
No, it means that this ratio of the original sequence divided by the one we came up with it did not give us a single finite positive number, did it?
No.
Because it diverged to positive infinity. And so when that happens, when the sequence we come up with ourselves, and you write down the original formula of the original sequence and divide it by the one you came up with, and then you take the limit, if you do not get a single finite positive number, well then all of this doesn't mean anything.
Okay.
The test failed. The test failed using our choice or pick of Cn. And which means is we need to pick a better choice. For what?
For C sub n.
Very good. Get it?
Got it.
Does that make sense?
Yeah. So all we're looking for is a positive single finite number. If not, all of that work went to waste.
Correct.
Okay.
And then we have to go back to the drawing board and come up with a different one. And if the one you pick next also doesn't give you a single finite positive number when you take the limit of these two, then it was all for waste again. Yeah?
Yeah.
So that's what can potentially make this series test not as desirable or a little bit abstract compared to the other ones. Okay?
Mm-hmm.
And I'm glad early on we understand that, because this was not a very difficult sequence formula for us to say, oh, it looks very comparable to 1 over n to the first.
Mm-hmm.
Some other ones that it's a little more tricky. Not a lot, but so that's, now I want to just do 1 or 2 more, but we already know all this stuff. And so the limit part goes quickly. So,
Okay.
so this one diverged. And so in this one, Denise, you're just gonna have to figure out what the formula is for
Okay.
A sub n. And I'm just gonna write this part down. All of them have a 1 again in the
Mhm.
numerator. All of them have a 200. And then it's plus, isn't this part the part that's changing? I mean,
Mhm.
200 plus 1. What's this one? 200 plus what?
8.
This one is 200 plus,
27.
and this is the part you just have to figure out the pattern of this part right here.
Mhm.
And there's gonna have to be an n in there.
Yeah.
And then I mean, I think it's reasonable to figure out what that n has to be, okay?
Okay.
And then once you figure that out, then you can compare it to something similar to this.
Okay.
Okay, so I'll leave that for you all. So for what's remaining, number 11 is interesting. Let me see. Number 11 and 7 are almost identical. So you can make yourself a note of that. And we'll do one of those. So let's do number 11. And trust me, when I say these now become not 30 minutes to talk about, maybe not even 3 minutes, okay? So
Okay.
number 11. Tangent of 1 over n. Okay. Oh, and I forgot. Oh, it's n equals 1, yeah. So what would happen, Denise, if we went right from the beginning and tried to look at the individual terms of the sequence? And if we, remember, they have to be getting smaller and smaller, converging to 0 to have any chance for its series to converge. So what would happen if we took the limit as n approaches infinity of this formula right here? What's 1 over infinity?
Infinity.
1 divided by a larger and larger and larger number.
0.
In tangent of 0 on our calculator or otherwise, it would be 0 without showing you the unit circle. And therefore, this series, when you start to add up the individual terms, they still have a chance to converge. They may not, but they have a chance. Is that okay?
Yes.
If now we have to say, well, we have to explore this further and use one of our series tests. This is not geometric, it's trigonometric. You cannot integrate tangent of 1 over n. If it was just tangent of n, well, then you could, but we can't integrate that. So the integral series test is out. It's not alternate, I have to think about that. It's not alternating. The tangent curve goes up and down, or goes up It's like the tangent graph, you know, it has these pieces to it. And some parts are negative and some parts are positive, and those cycles repeat forever, but it's not alternating. If you go from one dot to the next, it's not alternating from negative to positive all the time. So this is not alternating.
Mm-hmm.
You cannot use alternating series tests. The ratio test, if we wrote the n plus first term divided by the nth term, we would only have this. And taking the limit as n approaches infinity, there's nothing to cancel out here. And if you did take the limit, you would just get back to this we already did up here, and it was 0.
Mm-hmm.
This would also be 0. We would have 0 over 0. And when you use L'Hopital's and differentiate, I have to think a little bit about that. The derivative tangent of secant squared, you would get secant squared of 1 over n plus 1, secant squared of 1 over n times those derivatives, and that may work. I'm still trying to see it all in my mind. No, because when you ended up taking the limit again, you would get 0 over 0 again, and we would still be indeterminate. So trying the ratio series test and then proceeding with L'Hopital's will just put us in like an infinite loop of getting 0 over 0s. I know I didn't show all that, but I'm just asking you to believe me here. The root test, there is no nth power to take the nth root of so that it would cancel out. What's the only thing we have left is to try the limit comparison test and come up with another sequence that is somehow, and this is what I was telling you when we were talking about this, because now it's not so simple to say what's related to this.
Mm-hmm.
But we have to try. And if we try, Denise, and we don't get a single finite positive number, well then what? The test what?
Failed.
And then we would say what? We didn't pick a very good choice, did we?
No.
And we would have to try another one. Does that strategy make sense?
Yeah.
So that's what makes this frustrating, potentially. But it also works out very nicely as well, in most cases. What do you think would be worth trying, Denise? And we may be right, we may be wrong, but.
Well, to me, I'm just looking at the 1 over n, so that looks like a p-series.
Very good. That's a p-series. That's a very safe bet because we know what 1 over n does. It's a p-series that what?
A p-series that diverges.
And so we're going to find out momentarily when we take the limit, if we get a single positive finite number, well then we can say hooray, hurrah, and we can say that our choice was a good choice, and now we know what the original series does, huh?
Mm-hmm.
If we don't get a single finite positive number, then we'll be like, shucks, we picked the poor choice for C sub n. Or
Okay.
this test wasn't a very good one to use to begin with. That's the tough part, yeah? But
Yeah.
going to do that to us right here, okay? Because they're telling us to use it. Okay.
Okay.
So let's try. So what do we try now? And do
We
what?
try to take the limit
Mm-hmm. Of what?
of a sub n over c sub n.
And if we try to take the limit, we're hoping to get a determining value. If we get an indeterminate value, that doesn't mean we give up. That means we try to do whatever we're supposed to when you get a friendly indeterminate, or an unfriendly for that matter, and we'll proceed with it to see if we can get a determining value. If it turns out to be test failed, so be it. That's part of exploration. That's part of exploration, right? And
Yeah.
we try another choice, but we don't know until we try. Okay. Now, sometimes people might say, I'm going to put these terms in a calculator, write them down, and see if I start adding them up, does it seem like they're getting closer to some finite number, and therefore I have a sneaking suspicion that this is going to converge, and therefore I'm going to pick a partner that's similar that does converge, or if you think it's going to diverge, I'm going to pick something similar that's going to diverge. Sometimes that can save us a little bit of frustration of having to pick a new choice, but I think, I mean, a person can do that, or they say, this looks fairly reasonable, I'm going to try it and see what happens, you know?
Okay.
Okay. So what happens when we plug infinity in? 1 over infinity is what?
0.
Tangent of 0.
0.
1 over infinity is,
0.
so we get a friendly indeterminate.
Mm-hmm.
Now up here, I told you if we tried the ratio test, we would get a friendly indeterminate as well. The problem is this is messier to differentiate. Well, this is exactly the same as that one. However, the other one is not a tangent and it's only 1 over n. And if you think ahead a couple steps, what's going to happen when the derivative of 1 over n is that negative 1 over n squared we did earlier today?
Yeah.
And what's going to happen when you differentiate tangent of 1 over n? Well, you're going to get whatever trig function. The derivative tangent is secant squared of 1 over n. But the important part is the next part of that derivative, which is the times the derivative of the inside. And what's going to happen when you differentiate that derivative of that inside?
It's 1 over n squared.
It's that negative 1 over n squared, just like this one's going to be, isn't it?
Mm-hmm.
So what's going to happen on the top here and in the bottom here? You're going to have a negative 1 over n squared and a negative 1 over n squared here, aren't you?
Mm-hmm.
And what's going to happen to that?
That's going to go to 1.
And all that'll be left is the secant squared part, or whatever the trig function is.
Yeah.
And then that gives us a very good chance of getting a determining value and being done.
Okay.
And if we would have tried this, it's a whole different story because both of them are tangents and this inside is not the same as this inside. And then if you did keep going, you would see quickly that the derivative of this part inside and in this part, I mean, I can't say I see it perfectly well. Maybe it's possible and I'm missing something, but even if I am, if it did clean up okay and the parts divided out somehow, or we could simplify it, tangent of 0 is still 1. And did I say that right? No, it's still 0, and this would still be 0. So you would still get a 0 over 0 anyway, and you would still not be there in terms of getting a determining value. Where this more quickly gets us there. I can't say with 100% certainty that this won't make it eventually, but this is much, much more efficient. Yeah?
Yeah.
Okay. So, using L'Hopital's rule, you said the derivative of 1 over n is negative 1 over n squared. The derivative of tangent is secant squared of that inner function times the derivative of the inner function, and the derivative of 1 over n is the same as it was below, which is negative 1 over n squared. If we take the limit right now, that wouldn't be very smart because we would get 1 over infinity or negative 1 over infinity, which was 0 over 0, and we would be a friendly indeterminate again.
Mm-hmm.
So clearly, you want to divide those out first and make this a simpler expression inside in our hopes to get a determining value for the limit. These are not absolute values. There's no absolute value on this limit comparison test. I keep forgetting to mention, though, I should have said, and I apologize, these terms of these sequences have to be positive. And to be honest, really, if the first few terms are not positive, it's okay. As long as eventually, from a certain point on, they're positive forever, that's what really has to happen. Not only on the one they give us, but the one we come up with. But on most of these problems, they're all positive from the beginning anyway. I just wanted to throw that in there.
Okay.
So now take the limit of this and let's see if we still have indeterminate or we have a determining value. And if it is a determining value, which type of determining value is it? If we get infinity, negative infinity, oscillating, or we get a single finite number that's not positive, then we're like, dang it, we picked the wrong choice for C sub n. And we got to start again.
Okay.
If we get a positive single finite number, then we're content with our choice because this will work and we will get a result. So now, what happens when you put infinity here? 1 over infinity is what?
0.
Secant squared of 0. Depending on the type of calculator a person has, they could find that out. But secant is also 1 divided by cosine. And cosine of 0 is 1. 1 squared is 1. 1 divided by 1 is 1. So we get 1. So this limit is now determinable and we get 1. Now don't think test failed because then you'd be getting confused with the ratio and or the root series test, right?
Mm-hmm. So if I don't have like a very advanced like calculator, I could put 1 over cosine of 0
Well, you could
times
first,
1 over cosine of 0.
yes, or just put cosine of 0 only. And then whatever it tells you, then you square it.
Okay.
That would be even easier yet. But also, I don't know who your trigonometry teacher was, but if you pick, that was a joke, okay? Because it was, okay, for those that end up listening. What's cosine, Denise? What is the cosine ratio?
It's, what do you mean?
Like the definition of cosine is either adjacent over hypotenuse or x over r. And what's the radius? And this point right here, the one we're using is the circle with radius 1. So R is 1.
Mm-hmm.
If you wanted to pick a bigger, any other type of circle, you could. You would just have a different radius. But this is the easiest one to use. What's the x value right here at 0 radians? Here's 0 radians.
1.
So what's 1 over 1?
1.
And that's how you get cosine of 0 to be 1 by ourselves.
Okay.
And then what's squared would be 1 times 1, which is 1. 1 divided by 1 is 1.
Okay, cool.
So what happened now, we got to the ratio of the original sequence divided by the one that we came up with ourselves, our C sub n. We went through the efforts that it required to get the determining value of this limit. It turned out to be 1, which means this limit converges, but that's not all that we're interested in. We're interested in how does it converge, and it converges to a single positive finite number, and that's what gives us our ability to come up with a conclusion about the original sequence whose terms we want to add up forever and see if they converge or not, which is called a series. So now what can we say? So 1 is what? 1 is what kind of?
It is a positive finite numerical value.
And therefore, our series
Converges.
Yeah, and we could go back and write it again, this one, or just say our series, which means this one, your choice. What does it do?
It converges.
So be careful. Do we say it converges because this converged, or do we now have to look at what the relative we picked does?
I thought that's what we were doing.
And what did our relative do? What did 1 over n do that we picked, that you picked?
Oh, it diverges.
Uh-huh. So just because we get 1 here, which means this limiting value does converge to 1, and better yet, it's a positive single finite number. Yes, the limit of A sub n over C sub n converged to a single positive finite number. Yay, hurrah. Now, what that does for us is says, oh, now I can go back to my original series they gave us, and now I know this will either converge or diverge the same as the one we picked does. And
Okay.
what did this one we picked do? What does it do? What is this?
It diverges.
When you add up the terms forever and ever and ever?
Yes.
Therefore, this one also has to what?
Diverge.
Diverge. Our series diverges as C sub n does. Because C sub n does diverge, then our original series will do the same thing by or using the limit comparison test. Any questions there?
No.
So we go back to WebAssign. That was this one. So we know it diverges. Now they wanted us to just fill this part in. Which means, what do you think this means then? What are they asking us for, Denise?
They're asking for C sub n.
Ah. And there are cases where a person could pick more than one C sub n and it will still work correctly. But I think the problems they ask us to write down our choice of C sub n, it's going to be pretty obvious that it's one choice. And therefore, we won't have an issue, we shouldn't have an issue with WebAssign marking this box wrong. Does that make sense?
Mm-hmm.
So what are we going to put here?
1 over n.
Mhm. And then did they ask us to write down what this limit was right here?
No.
And if they did, we would have put what?
0.
What did this A sub n divided by C sub n, what did that determining limiting value become?
Oh, we got 1.
Yeah, which is positive, a single positive finite number, isn't it?
Yes.
They write it a little differently here, and they say your answer, let's call it L, or the determining limiting value L, and it's greater than 0, because we did get 1, and that is greater than 0, and that means it's a single, and when they write L, that means finite, kind of. And that's what we're supposed to interpret. That's why I don't like to write it that way. And the notes, I like to write the actual words, single positive finite number, okay?
Mm-hmm.
And therefore, we can use, then we do know, or we can conclude that the original, this formula, which added up the terms forever, which gives us a series, which is really what all this is saying, is also will do whatever this one did, which is diverge. Okay?
Okay.
And check. And I need to reset something here because it's showing all the answers. Okay. This is going to be very similar, Denise. So what are you going to compare this to?
1 over n.
Yeah.
Cool.
This one looks a little scary here. What do you think you're going to compare this one to?
P series?
What does 8 to the nth power sound like? What is it similar to? One over n to the p power is a p series. And the n is in the base and the p is the power, and then depending on if p is greater than 1 or less or equal to 1 and greater to 0, we know that the p series converges or diverges. But that's not what this is. This is not n to the 8th power. If this would have been switched around, Denise, and an 8 switched around, then you're right, it would have been similar to a p series with
Okay.
p equals 8. But is that it?
No.
What happens if you wrote 1 over 8 to the nth power? Because that's what this is. The plus 1 doesn't affect this very much. The 6, you could factor it out, or you can say it's just 6 times bigger than this 1 right here. So what kind of sequence is this one? And you can also write it like this, Denise, without 1. You can write it as 1/8 to the nth power.
Oh, okay, geometric?
Mm-hmm. So you kind of have to remember this 1, you can always include it back into the nth power. Yeah? Because 1 times
Okay.
1 times 1 times 1, a finite number of times is still 1. So what are we going to do for this one? Compare it to what right here, Denise?
Compare it to 1/8 to the nth.
And I'm going to change it. Okay, no, that's fine. Which is like 1/8 to the nth power. Yeah?
Yes.
I'm just going to, do I want to do that? No. So 1/8 to the nth, but realizing that that's what we're comparing it to.
Mm-hmm.
So on our paper, if we went through, this is similar. If we even had this 6 times 1/8 to the nth power, we could say it's geometric. But because there's this +1, now we cannot say this is geometric, but it's close. It's kind of similar to a geometric, yeah?
Okay.
So we cannot just use the geometric series test and be done. By the way, if you took the limit right off the bat, like we normally do, to look at the individual terms of the sequence, what would happen without, let's not write it down this time. If you just took the limit as n approaches infinity of just this formula to do the first step, to check, are the individual terms getting closer and closer to 0 or not? What would happen if you put infinity right here? 8 to the infinity is still infinity plus 1.
Infinity.
6 over a larger and larger number.
0.
And so that means we cannot just stop and use the nth term test for divergence and say this diverges, right?
Right.
And that means we have to proceed. And when we have to proceed, that means use one of the series tests. The first one we always think about is geometric. If this +1 wouldn't have been there, we could have used geometric series test. And we could have rewritten it like this. And this would have been the beginning term. That would have been our A. Our common ratio would have been 1/8. And then we could have taken the absolute value of R, which is 1/8. That is less than 1. And we could say the series converges and be done. That would have been the case if this +1 wouldn't have been there.
Okay.
However, we can say, you know what, I can come up and create my own new formula for a sequence that's very similar to this one, that I readily know if it converges or not, or diverges, and then use the limit comparison test and see if we're fortunate enough when we do take the limit of a sub n over c sub n, if we get a single positive finite number, then we made it. Does that make sense?
Yeah.
It does not mean that we might have been able to use another series test, but we could not have just used the geometric integral. I'd have to think about it. Probably, maybe not. Maybe we could use the integral series test, probably. Alternating, this is not alternating. There's no -1 to the n or something that makes it alternate. Ratio series test. If I'm thinking through all the steps correctly, which I think I am, we would get equal to 1. And then we would say test fails, and we would have to go back and look. Because whenever the one you have is very, very close to a p-series or a geometric, usually the ratio test will equal 1, and it fails, and you have to go back anyway. The root test would be nice if this +1 wasn't there, because then we could get rid of this nth power, but not. So now we're back to the comparison test. But I do believe the integral series test would work, but it's not that friendly. So if we can come up with another sequence formula, and if we then take the limit as of a sub n over c sub n, and we get a single positive finite number, then we're done. And the chances of that being quicker than maybe the integral series test, it's more likely this could be done faster. Yeah, but I mean, it's subjective. Okay, so what do you want to try here to be our relative here? And if it's not going to be a p-series, so you don't have to say 1 over n to something. It doesn't have to be a 1 on the top. If you want it to be, you can. If you want to compare it to what geometric sequence are we going to for sure compare it to? For sure, at least what common ratio?
1 over 8.
So we at least want this part for sure to be right here.
Okay.
If you want to put the 6 there, that's fine, because with geometric, you can have a first term, a beginning term out here in front. That's your a. So you can have it with the 6 or without the 6. Either way, it will work. So, and then instead of writing 1/8, we're just going to write 1 over 8 to the n, so that when we write the limit of a sub n over c sub n, these will cancel out a little easier. Yeah?
Or can we go back to the question really quick?
Yeah.
I just want to see how it looks. Oh, okay. Okay. I had it backwards.
So you decide for us. If you put the 6 there, then it's more likely the 6 will divide out. But it's up to us. As long as we get a single positive finite number, that's all that really matters. So it's your choice. So what do you want me to put? Do you want me to put a times 6 in front here, or just leave it as that?
No, just like that.
Okay. And this is a what? What kind of sequence is this? Is it a p-series or a geometric?
Geometric.
It's a geometric with, well, this itself is a sequence. But when you start adding all the terms up, it's a series. And the common ratio is 1/8, which I already have up here, which is less than 1. What happens when your common ratio r, absolute value of r, is less than 1? The series and when we mean the series, we mean this one.
Convergence?
Hmm. Is that okay?
Yeah.
Did you make it back to your notes where you found the geometric series test, or you didn't make it? And you were
No,
guessing?
yeah, I got that.
Okay.
But now that we're doing the geometric, can we put the 6 in the front
Yes.
still?
You mean on the C sub n?
Yeah.
I remember I was asking you, you can choose, because if it's a P series, then you don't have a choice. You have to put 1 over.
Mm-hmm.
If it's geometric, you can put that 6 there as well or not. And if we do put the 6 there, Denise, it's not going to affect what R is it? It's not going to affect the common ratio, is it?
No.
It's still going to be 1/8. And if you put the 6 there, that just means when we write A sub n over C sub n, the 6's will divide out as well. And if you don't, the 6's won't divide out, but that's not a problem because 6 is just a number, so it's not an issue. Which
Okay.
means when you take the limit of A sub n over C sub n, does it really matter, Denise, if we get an answer of 6 or 2 or 12 or something, as long as it's a single positive finite number? Isn't that all that it matters?
Mm-hmm.
So if you decide to put the 6 here and it divides out, you're just going to get a smaller positive finite number. And if you left the 6 out and you don't put the 6, that means when you write down A sub n over C sub n, this 6 will not divide out, but your limiting value at the end will just be 6 times bigger. But 6 times bigger is still going to be a positive finite number. It'll just be 6 times bigger than it would have been if you would have chose to put the 6 there. But either
Okay.
way, you're going to get a single positive finite number. That's all that matters, huh?
Mm-hmm.
Does that make sense?
A little, yeah.
Are we trying to find out if this converge? I mean, we did find out, but that's simple to find out. We just look at the common ratio. Aren't we just trying to figure out if this one converges or not? Isn't that our initial problem, our initial question? Yeah.
Yeah.
And aren't we gonna say, I'm gonna find something to compare it with? And remember I was telling you before up here, there's always gonna be possibly more than one choice of C sub n.
Mm-hmm.
And and in some cases, your C sub n that you choose and I choose might be different. Maybe yours has the times 6 and mine doesn't. But
I can write it as 1/8 to the n, right?
Yes.
Okay.
All that really matters is when we take the limit of A sub n over C sub n, we better get, whether it's my choice or your choice of a formula right here for C sub n. If your choice gives you a single finite positive number and my choice gets a single positive finite number, that's perfectly fine. Because in both cases, we're going to say this original problem here will converge because this one that I picked and you picked converge, even if mine was different than yours. As long as we both get a limit that's positive single number, it's just your number and my number will be a different positive single finite number is all.
Okay.
Is that okay?
Yeah.
Okay. So which one do you want to pick? Just this one?
Yeah.
Okay. So now we're going to try using the limit comparison test. And what limit are we gonna take?
The A sub n over C sub n?
And what is our A sub n?
6/8 to the n plus 1.
And what's our C sub n?
1 over 8 to the n.
And either we leave it just like this and take the limit. If we get a determining value, we're done already. If we don't and we get an indeterminate, well, then we have to manipulate it somehow. And what happens when you put an infinity down here? What's 8 to the infinity?
Infinity.
1 over a larger and larger number.
0.
And won't the same thing happen up here?
Mm-hmm.
So we get 0 over 0, which is a friendly indeterminate.
Yeah.
So we can either use L'Hopital's and try to differentiate this independently and this independently, or try to clean this up first. Well, this is not the simplest derivative. You have to use quotient rule. And so I don't think it's recommended to just go right to L'Hopital's rule and start differentiating. It may work, it just may be messy. Wouldn't it be better to try to change this from division to multiplication and see if we can simplify this?
Yeah.
Okay. So what are we gonna get when we try to simplify?
6 over 8 to the n plus 1 times 8 over 1.
8 to the n over 1. So far, so good?
Yes.
And what's going to happen if we try to take the limit right now? We did manipulate it. The question is, did we manipulate it enough? Or do we need to keep going? If you put infinity in here, you're going to get 8 to the infinity is infinity, times 6 is still infinity. 8 to the infinity, infinity plus 1 infinity, times 1 is still infinity. And now you would get not 0 over 0, but we would get infinity over infinity, and that's still indeterminate, isn't it?
Mm-hmm.
And we could use L'Hopital's here, and it's actually easier to use L'Hopital's rule here on the top and here on the bottom than it was up here. So that would be an improvement if we stopped right now and just said, I'm going to use the L'Hopital's rule and differentiate the top and the bottom. It would be less difficult than up here, than it was up here to differentiate. But maybe we can even avoid that. So let's put this together a little more closely and then see if we can do any more simplification. So I really haven't done anything different from here, except instead of two fractions, I just put it together as a single fraction.
Mm-hmm.
And if we take the limit, we're still going to get infinity over infinity. But what do you think we could do here other than differentiate?
Do we just divide everything by 8 to the n?
Very good. We sure do. I didn't really need to put those parentheses down, but divide everything by 8 to the n. Hoping that when we clean this up, we will not get a friendly indeterminate anymore, and especially not an unfriendly indeterminate, but a determinable form. And we hope that we picked a good choice for C sub n and we get a positive finite single number instead of something else. And that would be to start over again with a new choice of C sub n. So these divide out. These divide out to 1. 1 over 8 to the n does not divide out. But I hope we can look ahead and see that this is going to work out. So if we take the limit now, what's 8 to the infinity? That just becomes bigger and bigger to infinity. 1 over a bigger and bigger number converges to what?
0.
0 plus 1 is 1. 6 divided by 1 is what?
6.
6. The limit converges. And don't fall for, oh, that means this one converges. No, that means this test is going to work. It converges to a single positive finite value, which is very good news. Finite number or value, because we got a 6. But then don't fall for the trap, the potential trap. That means this automatically converges. No, this will do just like what does?
C sub n.
Yeah. And what could happen with C sub n? It could either converge, and then it will sound the same as this one, which is why the trap can occur to fall for, or if this one diverges, then this one also diverges. Yeah?
But this one converges.
Correct. Our series converges. As our C sub n did. We know our series converges by the limit comparison test. Now, Denise, we had that discussion about what if you would have put a 6 there, yeah? For our choice of C sub n. And what would have happened if we would have done that? Then what would have been right here on the top right here?
Oh, 6.
A 6.
Oh, and then where we would reciprocate it, those would cancel out.
Yep.
Okay.
What would happen when they cancel out? You would have these gone, but all you would have left here then is a 1 instead.
Yeah.
And then what would have happened when you took the limit? You wouldn't have gotten a 6. You would have gotten what?
1.
A 1. Isn't that still okay?
Yes.
Because are we terribly concerned about what positive number this A sub n over C sub n converges to, or as long as it's positive and finite?
As long as it's positive.
Is that okay?
Yes.
That's why there will be times when there's some flexibility in our choices for C sub n. And even though when you take the limit of A sub n over C sub n, maybe for one person's choice of C sub n, they get one single finite positive number, but someone else will get a different single positive finite number, and that's okay. Does that make sense now?
Yes.
Okay. So right here, they may not. They may mark us wrong, but I don't think they will. Or if I put a 6 there, they may mark us wrong, and then they're like, well, they should. Yeah?
Mhm.
Because either one's okay.
Okay.
So I'm just going to gamble here and put a 6 just to see what they do. Okay? What do you think they're going to do?
I think they're gonna counter right.
You're optimistic. You're right. What did they want? What did they list as their answer? What
8
is
to
this?
the negative n.
What does that really mean?
1 over 8n.
Yeah.
Okay.
Yeah?
Yeah.
What do you think,
Okay.
without us doing this problem, what do you think we're going to compare this to?
P series?
Good. And what? 1 over what?
N to the 4th?
Good try. If you did do that without me showing you, I'm just going to ask you to believe me. Then when you would write this down and take the limit, you would get, a limit of 0. And what would that do for us if we got a limit of 0 when we did A sub n over C sub n, if we would get 0?
Does the test fail?
Correct. Because we didn't pick a good choice. 1 over n to the 4th, I could show you and work it out, but I'm just gonna ask you to believe me here. And we would get 0, test fails, because we need to pick a better, closer choice for our C sub n.
Okay.
Can you think of a better one?
No. That was my only thought. Like there I'm already lost if it's not 1 over n to the 4th.
Well, is it just 1 over n to the 4th here, Denise, or is there something extra here?
Well, there's extra, but I thought we were trying to see which one it kind of looked like. And that's why I just
Good.
picked.
Good. You're correct. And sometimes the one we pick may not have been the right choice, and this wouldn't have been.
Okay.
Because what is n to the 4th times n? What is n to the 4th times n to the 1st power?
N to the 5th?
Mhm. So, and if you keep distributing, this part's probably potentially going to mess our mind up a little bit. So the question is, which is a subjective question, what is a closer choice for us to use for our C sub n? This one, because you see the 1 over n to the 4th, or, oh, I'm sorry, this is not C sub n. This is what this is. This is the original.
Mm-hmm.
Or pick 1 over n to the 5th as your P series.
Okay. The N to the 5th.
Yeah.
Okay.
And then you might say, well, I'm ignoring this part. That's true. But when you pick a P series to compare it with, you cannot pick, it has to be 1 over n to a power, and that's it. You can't have any extra stuff, yeah?
Okay.
So what part is more dominating here by writing n to the 4th on the bottom or n to the 5th?
N to the 5th.
And you're like, well, I wouldn't have known that. Well, okay. But if you would have done this, I mean, you can almost see it in your mind if you look at this. If you would have put 1 over n to the 4th here, Denise, what would have happened then? What would have been the next step?
To find the limit.
Good. What would have been 1 over infinity? This would be infinity on the bottom. What would that be?
0.
And what about the 1 over n to the 4th you would have written down?
That would have also been 0.
And then you would have gotten indeterminate, friendly, and then you would manipulate it. And how would you manipulate 1 over n to the 4th times n plus 3 over 1 to n to the 4th? What could you do with this 1 over n to the 4th?
Multiply it by the reciprocal.
Good, which would be?
N to the 4th over 1.
Very good. And what would happen, what would happen to the n to the 4th power over this n to the 4th power?
It would go to 1.
That's a miss, sorry. What would be left? 1 over what?
1 over n plus 3.
And what would that limit become?
1 over infinity.
Which is?
0.
And then you would have gotten your limit for a sub n over c sub n, and you would have gotten 0, huh? And then you would have looked at your notes or remember in your mind, what happens if you get the limit of a sub n over c sub n and you get 0?
The test fails.
Ah, and what does that mean? The test fails.
Then we have to try something else.
Something else for what?
For c sub n.
Uh-huh. Because the one we picked wasn't close enough.
Okay.
And so what are we saying instead? Pick 1 over what?
N fifth.
Mm-hmm. Is it okay?
Yeah.
Now, instead of me working this out any further, I'm just going to tell you, you're going to pick this. P is equal to 5, which makes this what kind of P series? Converging, diverging, what?
It's converging.
And then when you write this a sub n over c sub n, what's going to happen then? Right up here, when you reciprocate, it won't be n to the 4th over 1. It'll be n to the what?
5th over 1.
And what will happen to the n to the 5th and the n to the 4th?
It goes to n.
And all that will be left is n over what?
N plus 3, and then divide everything by n.
And then you're going to get what?
1 over 1 plus 3 over n.
Which is?
1.
And what does that tell us?
That it converges.
But because you got a positive single finite number, then that tells you what?
That
our series does the same as what?
as c sub n does.
Which is what?
Converge.
Yep. Make sense?
Yeah.
Nice, you can see all through that, huh?
Yeah, you really pushed me. I was trying to picture it in my head.
Well, you did it, and I'm very happy to see that you could do it. Okay, so you can finish that one. I mean, you already did it in your mind. This one, I'm just gonna say, this is 2 to the n and 7 to the n. They're both to the nth power. But when you have to come up with your own c sub n, what kind is this, Denise? 2 to the n. Is that P series or geometric?
Geometric.
And if you look at this together, and you're kind of coming up with one that you want to say, this is similar to what P series or similar to what geometric series, and we know it's geometric. Geometric is
Mhm.
something to the nth power.
Mm-hmm.
And what are we going to put inside here?
2/7.
And what kind of ratio is 2/7? When you take the absolute value of R, you get the absolute value of 2/7. 2/7. And that compares to less than 1.
Mm-hmm.
And what does that mean about this C sub n series? Or
It converges.
by the geometric series test. So now we're going to use this, as
Yeah.
your C sub n. But when you write it down right here, you don't want to leave it like this, because it's not going to help you very much when you try to cancel with these terms. But can't we just split this up and write it as 2 to the nth power and 7 to the nth power? Yeah?
Mm-hmm.
You see how this is the same as this?
Yes.
So that's what you want to put right here. Although they would give you credit if you put this one. But to help you find this determining limiting value of A sub n over C sub n, you're going to want to write it like this instead of this.
Okay.
And then when you reciprocate it, it's going to be 7 to the n over 2 to the n. And it's not going to be helpful to leave it like this, because you're going to get infinity over infinity. And without me doing the whole problem, you're going to want to separate this, the 2 to the n plus 1, and you're going to want to write underneath this, not the 7 to the n plus 1, but the 2 to the n. And that way you can divide them out. And then you want to put these together. So you're going to end up with 2 to the n plus 1 over 2 to the n, and then times 7 to the n over 7 to the n plus 1. You know, my mouse broke the other day because I use it so much on this lectures, especially writing here. And so I had to go find another mouse. Anyway, I'm sure you wanted to hear that. I only thought of that because I'm clicking all the time here. So is that going to be enough all by itself, or are you still going to get infinity over infinity?
Infinity over infinity.
So what are you going to want to do with this part and with this part?
You're going to divide it by, well, the first part you're going to divide it by 2n, 2 to the nth, and the other one by 7 to the n.
Very good.
Okay.
So you should be more than likely, should be very, very reasonable for anyone to proceed from there. Okay?
Okay. And will you still be having your office hour tomorrow in the morning?
Mm-hmm.
Okay.
I don't have any meetings tomorrow, and the last 4 or 5 days have been kind of difficult for me as coordinator, because they were asking for so many things that had to get done. But anyway, just a last couple of comments, and this looks scary right here. Well, let me say this first. This also looks scary. Maybe we'll wait until, well, this is n to the first power.
Mm-hmm.
Just like, was it enough on this one, Denise, to say my c sub n is going to be 1 over n to the fourth? Was that enough?
Mm-mm. We had to distribute the n to the fourth.
Yep. And this takes a little more acute observation to figure out what that's going to be. And it's not going to be c sub n equals 1 over n to the first power, because that won't be enough either. If you just pick this and put it down here, reciprocate, take the limit, the ends would cancel out and you would get 1 over this. And when you take the limit of 1 over this, you'll get 1 over infinity, which will be 0, and the test will fail because we didn't pick a good enough c sub n.
Okay.
So what is closest to this? What can we pick? Well, what is the square root of n to the 8th?
8 to the 8 halves.
Good. Which is? What is 8 halves reduced down to? What's
4.
8? 4. So this is very close to n to the 4th
Mm-hmm.
times the other n. And what's n times n to the 4th?
And 5th.
So that's what you're going to want to compare it with.
Okay, cool.
The only problem is, without me doing the whole problem, when we put right here 1 over the n to the 5th, that'll be correct. When you reciprocate it, you're going to get what up here, Denise? And what up here on the top?
And 5th over 1.
We don't really need the 1. What's going to happen to n to the 5th over n?
It becomes just n
To the what?
to the 4th.
So I'm kind of almost doing this with you without being very formal or neat at all. And now what will happen when you take the limit? You're still going to get infinity to the 4th power. That's still what?
Infinity.
And on the bottom will still be what?
Infinity.
And you don't want to do L'Hopital's here because this
No.
will be kind of a mess. So what you got to do is, you see this right here, Denise? N to the 4th?
Mm-hmm.
If you go backwards, what is it equal to? N to the what?
8 halves.
Which is also equal to what?
The square root of n to the 8th.
And that's the trick that would cause this problem to be different and potentially difficult, is that this n to the 4th is not going to be sufficient to leave it as that, to try to take the limit of this. So what you want to do is change that n to the 4th as the square root of n to the 8th. And that's the clever step required. And in the denominator, you still have n to the 8th plus 2. All this is still waiting for the limit. And still you'll get infinity over infinity, and that's still not enough. But aren't these both square roots now, Denise?
Mm-hmm.
And so instead of writing it twice, you can write it once.
Right.
And what's going to be in the numerator?
N to the 8th.
And the denominator?
n to the 8th plus 2. And then we just
Still not enough.
divide by n to the 8th.
Ah, there you go.
Okay.
Now you're catching on.
Yeah, that seems to be a pattern now.
Yep. So I'll let you finish that.
Okay.
What about this one then, Denise?
Mm. Would it be a P series?
Yep.
Okay, cool.
And which one?
Well, it's less than 1. So if it's less than 1.
Whoa. What would be your C sub n choice, you think?
Oh, I was doing 1 over, and then I put the denominator in parentheses, and I put it to the 1/2. So my P would be 1/2, or is that wrong?
Yeah, that would fail you because what this is not, this is a 2 right here,
Mm-hmm.
which is a square root, but this is not a 1 right here. What is this right here?
2.
So this is very close to the square root of n squared. Isn't the only
Okay.
thing different between this and this is the +9?
Yeah,
And what does this simplify to?
just 1 over n.
Ah,
Okay.
so there is your choice. And there's your P series. What's the
Okay.
value of P right here?
1.
Which means this one does what?
Converge? No, diverge.
Diverges. And then what are we going to write over here then?
1 over n.
Good. And then what's going to happen when you take the limit?
You're gonna multiply it by n over 1, or just by n. And it's gonna be n over the square root of n squared plus 9. And then would I rewrite my n as nth root of, no, I don't know.
Yes, you're almost there. How can we go backwards and write n in terms of of whatever root this is, which is a square root? N to the first power, you can write it inside a square root as what n? N to the what power?
1.
Is that
Okay, so it's gonna be
is
square
this?
root of n squared.
Uh-huh.
Okay.
And then here will be n squared. And then what are you going to do with this? Leave it like this? No, you'll still get infinity over infinity.
We're gonna put it together and then do the division of n by n squared of everything.
There you go. Well, that leaves us with one problem. What about this one? This minus 1 is up in the exponent position. So there's a parenthesis around that.
Okay.
What would happen, Denise, if we had n to the 4 minus 1? I'm just making an example. Over n to the 4th power plus 5. So instead of writing a k right here and a k right here, I put what instead? I just picked a number. What did I pick?
4,
And what is 4 minus 1?
3.
Now, this is our a sub n still. What do you think would be a good choice to pick for a c sub n?
It would be is that a power of 1?
I wrote question mark here.
Oh, okay. Well, that would just be 1n at the bottom.
Very good. Why is that?
Because the numerator took 3 from the denominator.
So this if you divide everything by n to the 3rd power, what would you get up here?
You'd get 1
Over
n
plus
plus 5
over
n
cubed.
Yes, over n cubed.
So this is our a sub n, like our original. So what's a good c sub n choice that's very close to that one? Just 1 over what?
N.
To the 1st power. Which is a p series? With p equals 1?
Yes.
And then when you write down the limit, I would leave it like this first and then write over 1, because then when you reciprocate it, it's going to simplify easier. Yeah.
Okay.
But we don't have a 4. By the way, what would happen if this would have been a 7 minus 1? And if this would have been a 7 instead?
Then it'd be n 6th over n 7th. So we'd be left with 1 over n as well, the same thing.
And what if this would have been any number, anything bigger than, oh, by the way, notice what it says here. K has to be greater than 2. So I pick 4, then we pick 7. If you pick 11, is it going to really matter?
No.
Because what's this on the bottom? K, and this is K minus 1. This is always going to be how many n's more than the one on top?
1 more.
1 more. So what are you going to pick right here for your choice of C sub n? You're going to pick
1
what?
over n.
Yeah? And then when
I'll
you
probably have some trouble with that one, but I'll try to figure it out.
and when you reciprocate it, it'll be times n to the 1st power over 1. Yeah? And I'll just give you this last hint. multiply n to the first times n to the k minus 1. Multiply that out. And whatever you get, you'll still have n to the k plus 5. And then see what you can do from there. So you
Okay.
multiply this, n to the k minus 1 times n to the 1. That'll be n to the something. And whatever that is, then clean this up, and then you're done.
Okay.
I mean, almost done. Very quickly, like this would turn out. Okay?
Mm-hmm.
Phew. I think we broke a record, and it's kind of sad. I feel bad. I'm just lost to know what else to do. And I feel bad for other people. Well, one, I feel bad for you. You have to sit here and listen and be patient. I feel bad for me. I get tired too.
Yeah.
But I don't know what else to do, because if I only would have spent, can you see why it's so difficult for me to try to make it through all these sections?
Yeah.
Um,
Just a lot to know.
a lot to know. I don't know how people will learn all this on their own if you don't give them this. I mean, maybe not this much, because I virtually helped you with every single one. But even if I spent 2 hours less, then that's still more than normal, and then that still makes it difficult, yeah, for a student.
Yeah.
So that's the most difficult thing always for me as a teacher at these levels of math, is to say, well, how much should be reasonable amount to help? And that's very difficult, yeah, for me at least.
Yeah.
But anyway, so I hope this gives you a very reasonable chance to finish everything. And if not, you can ask tomorrow or Friday, and on the office hour. And I will put a test in here tonight sometime over these 6 sections. Worst case scenario, if it's tomorrow morning, I hope I can be forgiven. And that'll be due next Tuesday night.
Okay.
And then as you asked me in the email and I responded on Sunday night, I will, from anytime after 6 p.m., I'll put the final in, and then everyone will have until Thursday night and pick a time frame to take it.
Okay.
And that's it. Okay, so that concludes this section for the moment, at least. And then if you have questions, you can ask tomorrow or Friday. Okay.
Okay. I will.
Okay, Denise. Well, thanks for your patience and your endurance. Okay.
Thank you.
You're welcome. And good luck with the rest, and we may talk soon or not. If you have any other questions or comment, then just email me, okay?
Okay. Thank you.
You're welcome. Have a nice rest of your Wednesday.
You too. Thank you. Bye-bye.
Goodbye.